Hello there, and welcome to Science for Sleep, a quiet place where curiosity slows down, ideas unfold gently, and science is allowed to wander at an unhurried pace. Tonight you do not need to solve anything, remember anything, or even stay awake for very long. All you need to do is listen, let the thoughts arrive and drift away again, and allow the story of the universe to move at its own steady speed. Before we ease into it, take a small moment to notice where you are. Are you listening from a bedroom with the lights already dimmed, or maybe from a couch where the day is finally loosening its grip? What time is it where you are right now? Late evening, early morning, or somewhere in between when the world feels especially quiet? It is a fitting question tonight, because this story revolves around time, distance, and numbers that refuse to line up neatly, no matter how carefully we measure them. If you find this calm exploration soothing, or if it helps your thoughts settle after a long day, you are always welcome to like the video or subscribe. It helps this gentle corner of science reach others who may also be searching for something slow, thoughtful, and reassuring. And now, with nothing else required of you, we can begin. Imagine for a moment that you are standing in a vast open field at night. There are no buildings, no streetlights, no familiar landmarks, just darkness above stretching in every direction, scattered with faint points of light. Some of those lights are close, some unimaginably far away, and every single one of them carries a story from the past. Astronomy, at its heart, is the act of listening to those stories and trying to piece them together into something coherent. For over a century, scientists have been doing exactly that. They have been measuring the universe, carefully, patiently, number by number, using the best tools available to them. They have weighed stars, timed explosions, tracked galaxies, and followed faint glows left over from the earliest moments after everything began. And for a long time, those measurements seem to tell a consistent story. The universe is expanding. Space itself is stretching. Galaxies are drifting apart, not because they are moving through space, but because space is growing between them. That much at least seemed clear. But then something subtle happened. As measurements improved and instruments became more precise, the numbers began to disagree. Not dramatically at first, not in a way that set off alarms or caused panic, just a quiet mismatch, small enough to be dismissed as error, yet persistent enough to refuse to go away. The universe, it seemed, was telling two slightly different stories about how fast it was expanding, and no matter how carefully scientists checked their work, those stories did not quite line up. This is where our journey begins, not with certainty, but with disagreement. To understand why this matters, it helps to step back and think about what it means to measure something as vast as the universe. On Earth, measurement feels straightforward. A ruler, a clock, a scale. Even when precision matters, the basic idea remains the same. You compare something unknown to something known, but the universe does not offer us that convenience. We cannot stretch a measuring tape from one galaxy to another. We cannot place a stopwatch at the edge of space and wait. Instead, astronomers rely on light. Light is the universe's messenger. It travels at a constant speed, it carries information about where it came from, and it remembers the conditions it passed through along the way. When we look into the night sky, we are not seeing things as they are right now. We are seeing them as they were, sometimes millions or even billions of years ago. A distant galaxy does not appear distant simply because it is far away. It appears distant because its light has taken an extraordinarily long time to reach us. By studying that light, astronomers can learn two crucial things. First, how far away an object is. Second, how fast it is moving relative to us. Combine those two pieces of information, and you can begin to describe how the universe is expanding. This relationship between distance and speed is captured in a single value known as the Hubble constant, named after Edwin Hubble. Despite the name, it is not really constant in the everyday sense. It is more like a snapshot, a number that tells us how fast the universe is expanding right now, at this particular moment in cosmic history. For decades, scientists have worked to refine this number. Early estimates were rough, uncertain by huge margins. Over time, with better telescopes and better methods, the uncertainty shrank. The hope was that eventually all measurements would converge on a single value, neat and precise, like the answer at the end of a well-behaved equation. That is not what happened. Instead, two different approaches to measuring the expansion of the universe began producing two different answers. Both methods were careful, both were sophisticated, both relied on solid physics. And yet when the numbers were compared, they stubbornly refused to match. This disagreement is now known as the Hubble tension, though the name makes it sound more dramatic than it feels from the inside. There was no sudden realization, no single moment when scientists gasped and stared at a chalkboard in disbelief. It unfolded gradually, through papers, conferences, reanalyses, and quiet discussions that stretched on for years. One way of measuring expansion looks at the nearby universe. It starts close to home, using stars and galaxies that are relatively near, at least by cosmic standards. Astronomers measure their distances using a carefully built chain of methods, each one calibrated against the next. This approach relies heavily on observations made by instruments like the Hubble Space Telescope, which has spent decades quietly circling Earth, free from the blurring effects of our atmosphere. The other way looks deep into the past. Instead of measuring distances directly, it studies the faint afterglow of the early universe, a nearly uniform background of radiation left over from a time when everything was hot, dense, and close together. By analysing subtle patterns in that ancient light, scientists can infer how the universe must have expanded over billions of years to arrive at the structure we see today. In principle, both methods should lead to the same answer. After all, they are describing the same universe, but in practice they do not. The difference is not enormous. It is not a factor of 2 or 10. It is a few kilometers per second per megaparsec, a unit that already sounds abstract enough to blur into meaninglessness. Yet the precision of modern measurements is such that this difference cannot be easily dismissed. The error bars do not overlap. The numbers stand apart quietly but firmly. At first, many assumed the issue would disappear with better data. Perhaps there was a calibration problem. Perhaps a subtle bias had gone unnoticed. Perhaps dust, gas, or instrumental quirks were skewing the results. These are reasonable assumptions, and scientists are trained to distrust surprising results until every mundane explanation has been exhausted. So they checked, and checked again. They reanalyzed data. They improved models. They cross-checked instruments. They used different stars, different galaxies, different statistical techniques. The measurements became sharper, more reliable, more constrained. And as that happened, the disagreement did not shrink. If anything, it became more pronounced. This is the moment when a scientific puzzle becomes interesting. Because when two well-supported methods disagree, there are only a few possibilities. One of them is wrong. Both of them are missing something. Or the underlying theory needs adjustment. None of these options are trivial, and none of them are comfortable. Yet they are also where progress often begins. To appreciate why this matters, consider what the expansion rate of the universe connects to. It influences estimates of the universe's age. It affects how structures like galaxies and clusters formed over time. It ties into the nature of dark energy, the mysterious component thought to be driving the accelerated expansion of space. A shift in this number ripples outward, touching nearly every corner of modern cosmology, and yet, despite its importance, the universe itself seems entirely unconcerned with our confusion. Galaxies continue to drift apart. Light continues to travel. Stars are born and die on schedule, indifferent to whether our equations balance. There is something quietly humbling about that. As listeners, we're used to stories where mysteries are resolved, where contradictions are explained away, where clarity eventually arrives. Science does that sometimes, but not always quickly, and not always in a straight line. More often, It proceeds by noticing small inconsistencies and refusing to ignore them. The story we are beginning tonight is not about failure. It is about precision. It is about what happens when our tools become good enough to reveal cracks in our understanding. The universe is not misbehaving. It is behaving exactly as it always has. It is our descriptions that are being tested. You might find it comforting to know that this kind of disagreement is not unusual in science. Many of the most important advances began as small tensions between theory and observation. The orbit of Mercury did not quite match predictions. The behaviour of light did not fit classical expectations. In each case, the mismatch was not a mistake to be erased, but a clue pointing towards something deeper. So when we say that the universe disagreed with itself, what we really mean is that our measurements are asking a question we do not yet fully know how to answer. There is no urgency here. The cosmos has been expanding for billions of years. It will continue doing so whether we resolve this puzzle tomorrow or a century from now. This gives us permission to slow down, to explore the problem carefully, and to accept uncertainty as part of the process. For now, it is enough to sit with the idea that even with all our technology, all our equations and all our confidence, the universe can still surprise us. It can still whisper, gently but persistently, that there is more to understand. Long before anyone suspected that space itself could stretch, the night sky appeared calm, orderly, and reassuringly still. If you stepped outside on a clear evening centuries ago, you would have seen the same familiar patterns humans had always seen. Stars rose in the east, set in the west, and returned again the next night in nearly the same places. Constellations held their shapes. The heavens felt permanent, like a painted ceiling arching endlessly overhead. Nothing about that quiet, repeating display suggested motion on the grandest scale imaginable. For most of human history, the idea that the universe could be changing in any deep structural way would have felt unnecessary, even strange. Change belonged to Earth. Seasons shifted, rivers moved, lives began and ended. The sky, by contrast, seemed immune to all of that. Philosophers and astronomers alike described the cosmos as eternal and unaltered, a backdrop against which human affairs played out. Even when planets wandered slowly against the stars, their motions were predictable, looping back again and again, as if following carefully rehearsed paths. This sense of cosmic stillness carried well into the age of early telescopes. When astronomers first began pointing lenses upward, they discovered far more detail than the naked eye could see, but not yet any sign that the universe itself was growing. They found moons around Jupiter, rings around Saturn, and faint cloudy patches that would later be called nebulae. These discoveries expanded the known contents of the universe, but they did not fundamentally change its perceived behaviour. Space, as far as anyone could tell, was simply there. Even as physics advanced, the assumption of a static universe lingered. When gravity was formalised into precise mathematical laws, it described how objects moved within space, not how space itself might behave. Stars pulled on one another, planets orbited, everything fit comfortably within a cosmic framework that felt stable and unchanging. The universe had structure, but no apparent storyline. That began to shift quietly in the early 20th century, not through philosophy or speculation, but through measurement. Astronomy was becoming more quantitative. Telescopes were larger, photographic plates more sensitive, and spectroscopy was opening a new way of reading light. Instead of simply recording where objects were, astronomers could now examine how their light was distributed across different wavelengths. Hidden within those patterns were clues about motion, composition, and distance. Light, it turned out, was far more informative than it appeared. When light passes through a prism or diffraction grating, it spreads out into a spectrum, revealing dark or bright lines corresponding to specific elements. These spectral lines act like fingerprints, allowing scientists to identify what stars and galaxies are made of. But they also do something else. They shift. If an object is moving toward us, its spectral lines shift slightly toward shorter wavelengths, a phenomenon known as blue shift. If it is moving away, they shift toward longer wavelengths, creating a redshift. At first, these shifts were used mainly to study stars within our own galaxy. Astronomers measured how fast stars orbited the Milky Way's centre, or moved relative to the Sun. The idea that entire galaxies might be moving, let alone that space itself might be stretching, was not yet on the table. Then attention turned outward. Those faint nebulae, once thought to be clouds of gas within the Milky Way, began to reveal their true nature. Some were spiral-shaped, others elliptical, and their light showed patterns that did not quite match what was expected from nearby objects. As distances were estimated more carefully, it became clear that many of these objects lay far beyond the boundaries of our own galaxy. They were galaxies in their own right, vast collections of stars separated from us by enormous gulfs of space. With that realization, the scale of the universe expanded dramatically. The Milky Way was no longer the entirety of existence. It was one island among countless others, scattered across a cosmic ocean. Once galaxies were recognized as independent systems, their motions became a subject of interest. When astronomers examined their spectra, they noticed something remarkable. The vast majority of galaxies showed redshifted light. Not just a few, almost all of them. And the farther away a galaxy appeared to be, the greater its redshift tended to be. This pattern was subtle at first and easy to misinterpret. Measurement errors were common, distances were uncertain. Yet as data accumulated, the trend became harder to ignore. Galaxies were not merely moving randomly, they seemed to be receding from us in an organized way. This observation did not immediately lead to the conclusion that the universe was expanding. In fact, the idea initially felt counterintuitive. If galaxies were moving away, where were they moving from? Was our location special? Were we at the center of some enormous explosion? The answer, as it slowly emerged, was far stranger and far more elegant. To understand it, imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single dot sits at the center of the expansion. From any one dot's perspective, all others appear to be receding. The motion is not through the surface, but of the surface itself stretching. In this analogy, the balloon surface represents space, and the dots represent galaxies. The expansion of the universe works in a similar way, though without an edge or an outside. Space itself stretches, carrying galaxies along with it. They are not flying through space away from a central point. The space between them is increasing everywhere at once. This idea required a shift in how people thought about motion and distance. It also required a willingness to let go of the comforting notion that the cosmos was static. The universe was not a fixed stage. It was dynamic, evolving, changing over time. Importantly, this expansion was not something anyone had set out to find. It emerged from careful observation and reluctant acceptance. Astronomers did not wake up one morning expecting the universe to be growing. They noticed patterns, checked them, argued over them, and gradually realized that the simplest explanation involved expansion. Theory followed observation. Around the same time these measurements were being made, equations describing gravity on cosmic scales were being developed. When applied to the universe as a whole, those equations naturally allowed for solutions in which space expanded or contracted. A static universe turned out to be unstable, requiring delicate balancing to remain unchanged. Once that mathematical door was opened, the observational evidence gained a theoretical home. What is striking is how calm this realization was. There was no single dramatic announcement that changed everything overnight. Instead, understanding accumulated slowly. Papers were published, distances recalibrated, spectra remeasured. Gradually, the idea that the universe was expanding became not just plausible, but unavoidable. For anyone living through that transition, the night sky must have taken on a new character. Those quiet points of light were no longer fixed markers in an eternal arrangement. They were participants in a grand, ongoing process. Every photon arriving at a telescope carried evidence that space itself had been stretching during its journey. This realization also introduced a new way of thinking about cosmic history. If the universe was expanding now, then in the past it must have been smaller, denser, and hotter. Expansion implied a beginning of sorts, not necessarily a moment in time that could be easily described, but a direction, a narrative. The cosmos had a past that was meaningfully different from its present. Yet at this stage, the focus was not on origins, it was on measurement. How fast was the universe expanding? Could that speed be quantified? Could it be used to estimate the universe's age or predict its future? Early attempts to answer these questions were crude by modern standards. Distances were uncertain by large factors. Estimates of expansion varied widely. Some implied a universe younger than the Earth itself, an obvious problem. Others suggested much longer timescales. Precision was elusive. Still, the core idea held. The universe was not static. The night sky was not frozen. Something vast and subtle was unfolding across incomprehensible distances. As decades passed, techniques improved. Astronomers developed better ways to gauge distances, building what became known as a distance ladder. Nearby objects could be measured directly using geometry. Those measurements calibrated brighter objects that could be seen farther away. Step by step, the reach extended deeper into space. Each rung of that ladder depended on the one below it. Any error could propagate upward. This made astronomers cautious, meticulous, and sometimes frustrated. But it also gave them confidence that, with enough care, the expansion of the universe could be pinned down numerically. Throughout all of this, one assumption remained largely unquestioned. No matter how it was measured, the expansion rate should be the same. Different methods might be noisy or imprecise, but as errors shrank, they should converge on a single value. The universe, after all, was one universe. That assumption would eventually be tested. At this point in the story, it is worth pausing to notice how quietly transformative this period was. There were no images of expansion, no animations, no sweeping visuals, just faint smudges on photographic plates, tiny shifts in spectral lines, and long nights spent comparing numbers. The universe revealed its growth not through spectacle, but through patience. Even now, when we speak of expansion, it is easy to imagine something dramatic. Galaxies rushing apart, space tearing open. In reality, the expansion is gentle on human scales. Bound systems like galaxies, solar systems, and atoms are unaffected. The stretching happens in the vast emptiness between structures, where gravity is weak and distances are enormous. This subtlety is part of why it took so long to recognize. Expansion does not announce itself loudly. It reveals itself only when you look far enough and measure carefully enough. As our understanding deepened, the expanding universe became a foundation of modern cosmology. It framed questions about dark energy, cosmic fate, and the large-scale structure of space. It also set the stage for the puzzle we are slowly approaching, the realization that measuring this expansion is not as straightforward as once hoped. For now, though, it is enough to sit with the idea that the night sky is not a static dome, but a dynamic, stretching expanse. Every distant galaxy is slightly farther away than it was a moment ago. Every beam of light arriving at Earth has been subtly altered by the growth of space along its path. This knowledge does not change the way the stars look to the eye. The constellations remain familiar. The darkness remains deep. But beneath that calm surface, the universe is in motion, expanding steadily, carrying with it the seeds of both understanding and confusion. At the beginning of the 20th century, astronomy was changing its character. It was becoming less about careful sketches and philosophical debate, and more about data, photographs, and measurement. Telescopes were growing larger. Glass plates were replacing the human eye as the final authority on what the sky contained. And quietly, almost without ceremony, the universe was preparing to reveal that it was far bigger and far less settled than anyone had imagined. Edwin Hubble entered this moment of transition without the air of a revolutionary. He was not trying to overturn cosmic assumptions or rewrite the nature of reality. In fact, much of his early work was methodical to the point of seeming ordinary. He observed, catalogued, compared, and classified. Yet it was precisely this steady, careful approach that allowed something extraordinary to emerge. Before his work reshaped astronomy, the prevailing view was still deeply uncertain about the true scale of the cosmos. The Milky Way was known to be large, but how large was unclear. Those faint spiral-shaped nebulae scattered across the sky were especially puzzling. Some astronomers argued they were nearby clouds of gas, forming stars within our own galaxy. Others suspected they might be distant systems of stars in their own right, but proof was elusive. The disagreement was not trivial. If those nebulae were inside the Milky Way, then our galaxy might be the bulk of the universe. If they were outside it, then the universe was vastly larger than anyone had comfortably accepted. Resolving this question required not opinion, but distance. And distance, in astronomy, is one of the hardest things to measure. Hubble's contribution began with a type of star that, at first glance, looks unremarkable. Cepheid variable stars are pulsating stars whose brightness rises and falls in a regular cycle. What makes them special is a simple, reliable relationship between how fast they pulse and how bright they truly are. By observing how bright a cepheid appears from Earth and comparing it to how bright it must actually be, astronomers can calculate its distance. This relationship had been discovered earlier, but Hubble was among those who applied it decisively to the problem of the nebulae. Using powerful telescopes, he identified Cepheid variables within the Andromeda Nebula. When he calculated their distances, the result was unavoidable. Andromeda was far beyond the boundaries of the Milky Way. In that moment, the universe expanded dramatically in the human imagination. The Milky Way was no longer the whole story. It was one galaxy among many, separated from others by distances so large they strained comprehension. What had once seemed like faint smudges were now understood as enormous systems of stars, each containing billions of suns. This discovery alone would have secured Hubble's place in astronomical history, but it was only the beginning. Once galaxies were recognized as independent entities, a new question arose naturally. How were they moving? Were they drifting randomly, held loosely by gravity, or was there some larger pattern at work? Answering this required combining distance measurements with information about motion, and once again, light provided the key. By studying the spectra of galaxies, astronomers could determine whether their light was shifted toward the red or blue end of the spectrum. These shifts indicated motion away from or toward the observer. When Hubble compared the distances of galaxies with their redshifts, a pattern began to emerge. The farther away a galaxy was, the faster it appeared to be receding. At first, this relationship was tentative. The data were noisy, distance measurements were still uncertain, and redshifts could be misinterpreted. But as more galaxies were added to the sample, the trend grew clearer. There was a roughly linear relationship between distance and recessional velocity. Double the distance, and the speed at which the galaxy was moving away roughly doubled as well. This was not the behaviour one would expect from galaxies simply flying outward through static space. Instead, it suggested something more profound. Space itself was stretching, carrying galaxies along with it. The universe was expanding uniformly, not from a single centre, but everywhere at once. This relationship would later be formalised into what is now known as Hubble's law. It provided the first quantitative evidence that the universe was not static, but dynamic, changing over time. The night sky, long thought to be fixed, was revealed as part of an unfolding process. It is worth emphasising how restrained this conclusion was at the time. Hubble himself was cautious. He spoke of apparent velocities and observational correlations, not cosmic origins or explosive beginnings. The idea that expansion implied a denser past was not his primary focus. His work was grounded in what the data showed, and the data showed a consistent stretching. That restraint mattered. Science advances most reliably when claims stay close to evidence, and Hubble's careful phrasing allowed others to build upon his results without overextending them. Theoretical physicists could take the observational relationship and explore its implications, while astronomers continued refining the measurements themselves. One of the remarkable features of this discovery is how it avoided spectacle. There was no visual sign of expansion. Galaxies did not appear to move from one night to the next. The effect revealed itself only through careful comparison of numbers gathered over long periods. It was the kind of discovery that rewards patience rather than excitement. As measurements improved, the slope of the distance-velocity relationship became increasingly important. This slope represented the expansion rate of the universe. A steeper slope meant faster expansion. A shallower one implied slower growth. Determining this value accurately became a central goal of observational cosmology. Early estimates of the expansion rate varied widely. Some suggested a universe only a few billion years old, which conflicted with geological evidence from Earth. Others implied much older ages. These discrepancies were not surprising given the challenges involved. Each distance measurement depended on calibrations that could introduce systematic errors. Still, the basic picture held. Galaxies farther away were receding faster. Space was stretching. This realization quietly reshaped how humanity understood its place in the cosmos. The universe was no longer a static container in which events happened. It was an active participant, evolving alongside the matter and energy within it. The past was not just different in detail, but fundamentally different in scale and density. Yet for all its significance, this expansion did not feel dramatic in daily life. The solar system remained stable, atoms remained intact, gravity held galaxies together internally. Expansion operated on scales so vast that it was invisible except through careful analysis. This made it easy to accept intellectually without feeling emotionally unsettling. Over time, Hubble's work became a cornerstone of modern cosmology. It set the stage for later discoveries, including the cosmic microwave background and the accelerating expansion driven by dark energy. But it also introduced a subtle dependence on measurement technique that would later become important. The expansion rate was not something directly observed in a single experiment. It was inferred through a chain of reasoning that connected light, distance, and motion. Each link in that chain had its own uncertainties. As techniques improved, astronomers revisited earlier assumptions, recalibrated distances, and refined models. For many years, this process moved steadily toward convergence. Estimates of the expansion rate narrowed. Confidence grew. The sense was that the universe's behavior was being pinned down more precisely with each new dataset. And yet, embedded within that progress was the possibility of disagreement. Because as measurements became more precise, small differences mattered more. Two methods that once seemed consistent within large error margins could begin to diverge as those margins shrank. A discrepancy that would have been invisible decades earlier could become impossible to ignore. This is where the legacy of those first measurements becomes especially relevant. The relationship Hubble uncovered did not specify how the expansion rate might change over time, nor did it guarantee that all methods of measuring it would agree perfectly. It simply established that expansion existed and that it followed a measurable pattern. The universe, it turned out, was more nuanced than a single number could capture easily. As you let this settle in, there is no need to hold on to the technical details. What matters is the arc of the story. A careful observer measures distances. Those distances reveal a pattern. That pattern transforms our understanding of the cosmos, and embedded within that transformation is the seed of a future puzzle. The expanding universe, once revealed, becomes something we want to understand ever more precisely. We refine tools, we extend reach, we compare methods, and in doing so, we discover that the universe does not always give the same answer twice in the same way. Light does not arrive quietly. Even when it looks soft to the eye, even when it barely lifts itself out of the darkness, it carries an extraordinary amount of information. Every photon that reaches a telescope has a history. It remembers where it came from, how energetic it was when it began its journey, and how that energy changed as it travelled across space. Long before anyone understood the universe was expanding, that memory was already embedded in the light itself, waiting to be read. To appreciate why redshift became such a powerful clue, it helps to slow down and think about what light really is. Light behaves as a wave, stretching and compressing as it moves. The distance between those stretches is called wavelength. Short wavelengths correspond to higher energy light, like blue or ultraviolet. Longer wavelengths carry less energy and appear redder. This is not an artistic description. It is a physical property that can be measured with precision. When light is emitted by an atom, it does so at very specific wavelengths. Each element produces a distinct pattern, a set of lines that appear at exact positions when the light is spread into a spectrum. These patterns are reliable. Hydrogen always produces the same lines. So does oxygen, sodium, iron, and every other element found in stars and galaxies. This consistency is what allows astronomers to identify the composition of distant objects, but those same lines can shift. If a source of light is moving toward an observer, the waves get slightly compressed, pushing the wavelengths toward the blue end of the spectrum. If the source is moving away, the waves stretch out, shifting toward red. This effect had been understood in sound long before it was applied to light. A passing siren sounds higher in pitch as it approaches and lower as it recedes. Light behaves in an analogous way, though the effect is far subtler and requires careful measurement. In the early days of spectroscopy, astronomers noticed these shifts in stars. Some stars showed blue shift, others red shift, indicating motion within the Milky Way. These observations were useful, but they did not yet hint at anything cosmic in scale. Stars orbit within galaxies. Motion was expected. The surprise came when this same technique was applied to galaxies beyond the Milky Way. When astronomers examined the spectra of distant galaxies, they found something striking. The familiar spectral lines were still there, unmistakable in their pattern, but they were displaced. Almost without exception, they were shifted toward the red. The farther away the galaxy appeared to be, the farther its lines were shifted. At first, this could be interpreted as ordinary motion. Perhaps galaxies were simply moving away from us through space. But that explanation quickly grew uncomfortable. Why would nearly all galaxies be receding? And why would their speeds increase so smoothly with distance? This is where redshift stopped being a curiosity and became a revelation. If the redshift were caused only by galaxies moving through static space, then our location would be special. We would be near the centre of some grand dispersal, watching everything flee outward. Yet observations did not support a preferred direction or centre. From every vantage point examined, the pattern looked the same. Galaxies receded from each other uniformly. A different interpretation fit better. Space itself was stretching, and light travelling through that space was being stretched along with it. As a photon crossed the universe, the fabric of space gently expanded, increasing the photon's wavelength. By the time it reached us, it appeared redshifted, not because the galaxy was racing away through space, but because the space between us and the galaxy had grown during the photon's journey. This idea takes a moment to sink in, and it is perfectly fine if it feels unintuitive. We're used to thinking of motion as something objects do. Expansion, in this sense, is something space does. Galaxies are not the primary actors, they are passengers. Redshift, then, became a way of reading the universe's expansion history. Measure how stretched the light is, and you can infer how much space expanded while the light was travelling. Combine that with an estimate of distance, and you gain insight into the rate at which the universe is growing. What makes this especially powerful is that redshift can be measured with extreme precision. Spectral lines can be identified to many decimal places. Even tiny shifts can be detected. This allowed astronomers to quantify recessional velocities long before they had equally precise distance measurements. In practice, this meant that redshift data accumulated quickly and reliably. Distances, by contrast, remained stubbornly difficult. You could measure a galaxy's redshift accurately, but translating that into a precise distance required additional assumptions and methods. This imbalance shaped cosmology for decades. At low redshifts, relatively nearby galaxies, the relationship between redshift and distance appears linear. Double the distance, double the redshift. This simple relationship made it tempting to treat redshift as a proxy for distance. In many cases, that approximation worked reasonably well. However, redshift is not just a measure of distance, it is also a measure of time. When you observe a highly redshifted galaxy, you're seeing it as it was when the universe was much younger. The light left the galaxy billions of years ago, when space was denser and expansion behaved differently. As a result, redshift encodes information not only about where something is, but when it is. This dual role complicates interpretation. A given redshift does not correspond to a single fixed distance in a simple way. It depends on the expansion history of the universe, which in turn depends on its contents, matter, radiation, and whatever else may be influencing cosmic growth. Early on, these complications were not fully appreciated. The first uses of redshift focused on establishing expansion, not on extracting fine details. But as precision increased, the subtleties became unavoidable. Another important distinction emerged between different kinds of redshift. There is the familiar Doppler redshift, caused by motion through space. There is gravitational redshift, caused by light climbing out of a gravitational well. And there is cosmological redshift, caused by the expansion of space itself. In the nearby universe, these effects can overlap. Untangling them requires careful modelling. For distant galaxies, cosmological redshift dominates. The stretching of space overwhelms local motions. This makes redshift an especially clean probe of large-scale behaviour. Yet it also means that interpreting redshift correctly depends on having a reliable model of how the universe expands. Here, a quiet circularity appears. To understand redshift, you need to know the expansion history. To determine the expansion history, you rely on redshift. This is not a flaw, but it does mean that assumptions matter. Different assumptions can lead to slightly different conclusions. As astronomers pushed their observations deeper, they encountered light that had been stretched dramatically. Galaxies at high redshift appeared faint, small and distorted by intervening matter. Their spectra shifted far into the red and infrared. Observing them required new instruments and new techniques. Despite these challenges, redshift measurements remained among the most reliable tools available. They provided a consistent, repeatable way to compare galaxies across enormous spans of space and time. No matter how uncertain distances might be, redshifts could be trusted. This reliability is part of what made later disagreements so surprising. When different methods of measuring cosmic expansion began to diverge, redshift itself was not the culprit. The spectral measurements were solid. The gentle stretching of light was not in doubt. The tension arose when redshift-based inferences were combined with other measurements to produce a single number describing expansion today. In some approaches, redshift data were interpreted through models that traced expansion from the early universe to the present. In others, redshift was paired with direct distance indicators in the nearby universe. Both used the same fundamental phenomenon, the stretching of light, but in different contexts. The fact that they did not agree suggested that the issue lay not with redshift as an observation, but with how its meaning was being translated into a single, present-day expansion rate. There is something almost poetic in that. Though we will keep our feet firmly on the ground, light travels faithfully. It stretches exactly as space stretches. It does not introduce ambiguity on its own. The ambiguity enters when we ask it to answer questions that depend on everything else the universe has been doing along the way. For listeners, it may be comforting to remember that redshift is not an abstraction invented to confuse. It is a direct, measurable feature of light. Astronomers do not imagine it. They record it. They see spectral lines displaced in ways that can be quantified precisely. The challenge lies in interpretation, not detection. As instruments improved, redshift surveys mapped millions of galaxies, revealing the large-scale structure of the universe. Filaments, voids, clusters, all traced through the systematic stretching of light. These maps confirm that expansion is not chaotic. It is remarkably uniform on large scales. Uniform does not mean simple, though. When you trace redshift back far enough, you encounter the early universe where conditions were radically different. Matter and radiation interacted intensely. Expansion rates changed over time. Dark energy, whatever its nature, became dominant only relatively recently in cosmic history. This means that the redshift you observe today is the result of a long cumulative process. It is not a snapshot of motion at a single moment, but a record of everything that happened along the photon's path. It is enough to appreciate the quiet power of this phenomenon. A gentle reddening of light, almost imperceptible to the eye, revealed that the universe is not standing still. It is stretching steadily and everywhere, carrying with it galaxies, histories, and questions that grow more interesting the closer we look. Knowing that the universe is expanding is one thing. Figuring out how fast it is expanding is something else entirely. The difference between those two questions may seem subtle at first, but it is where cosmology shifts from a broad realization to a precise science. Expansion by itself is a concept. Expansion with a number attached becomes a test of our understanding of reality. Once astronomers accepted that galaxies were receding from one another, because space itself was stretching, the next natural step was to quantify that stretching. How much space was added over a given amount of time? Was the expansion gentle or rapid? Did it proceed at a steady pace, or did it change as the universe aged? These were not philosophical questions, they were numerical ones, and answering them required building a ruler large enough to span the cosmos. On Earth, measuring speed is straightforward. You mark a distance, measure how long it takes to cross, and divide one by the other. In the universe, neither part of that equation comes easily. Distances are enormous and indirect. Time spans billions of years. Nothing can be tracked continuously from start to finish. Instead, astronomers are forced to infer speed by comparing snapshots taken at different distances, which also correspond to different moments in the past. This is where the idea of a cosmic ruler begins. The basic insight behind measuring expansion speed is simple. If you can determine how far away a galaxy is, and you can measure how fast it is receding from us, then you can calculate the rate of expansion. Do this for many galaxies at many distances, and a pattern emerges. The slope of that pattern is the expansion rate. In practice, every part of this process is challenging. Measuring how fast a galaxy is receding is the easier half. Redshift provides that information directly. The shift in spectral lines can be translated into a velocity with high precision. For nearby galaxies, this velocity behaves much like an ordinary speed. For distant galaxies, it reflects the cumulative expansion of space. Either way, redshift gives astronomers a reliable handle on motion. Distance, however, is far more elusive. You cannot simply look at a galaxy and know how far away it is. Brightness alone is not enough, because galaxies come in many sizes and luminosities. A small nearby galaxy can appear similar to a large distant one. To untangle this, astronomers rely on objects whose true brightness is known, or can be inferred, allowing apparent brightness to be converted into distance. This is the foundation of what is often called the cosmic distance ladder. The metaphor is apt, because each method of measuring distance builds on the previous one. You start close with techniques that work only in the nearby universe. Those calibrate methods that reach farther. Those in turn enable measurements at truly cosmic scales. The lowest rungs of this ladder rely on geometry. For nearby stars, astronomers can use parallax, the apparent shift in position as Earth moves around the Sun. This method is simple in principle and extremely reliable, but it only works for stars relatively close to us. Beyond that, the shift becomes too small to detect accurately. Once distances to nearby stars are known, they can be used to calibrate other indicators, such as certain types of variable stars whose intrinsic brightness follows predictable patterns. These objects act as standard candles, cosmic light sources with known wattage. Measure how dim they appear, and you can infer how far away they must be. Each step outward introduces more uncertainty. Dust can dim light, stellar populations can vary, calibration errors can creep in. Astronomers are acutely aware of these issues and spend enormous effort correcting for them. Still, no rung of the ladder is perfect. The strength of the method lies in careful cross-checking and redundancy. Once distances to nearby galaxies can be measured, redshift data can be paired with those distances. Plotting recessional velocity against distance reveals a line. The slope of that line is what we call the Hubble constant. It tells us how many kilometers per second of recessional speed correspond to each megaparsec of distance. Although the units may sound arcane, the idea is straightforward. The larger the Hubble constant, the faster the universe is expanding today. A smaller value implies slower expansion. Early measurements of this number were wildly uncertain. Initial estimates placed it far higher than modern values, implying a universe much younger than it actually is. Over time, as distance measurements improved, the estimated expansion rate decreased and stabilized. By the late 20th century, astronomers believed they were closing in on a reliable value. This progress created a sense of confidence. The cosmic ruler, while imperfect, seemed to be improving steadily. Each new generation of telescopes refined distances, reduced errors, and tightened constraints. The expectation was that all reasonable methods would eventually agree. That expectation turned out to be premature. As techniques improved, two broad approaches to measuring expansion speed emerged. One focused on the nearby universe, building the distance ladder step by step and pairing those distances with redshift measurements. The other relied on observations of the early universe, using relic radiation to infer how expansion must have proceeded over cosmic time. Both approaches were sophisticated. Both were grounded in well-tested physics, and both were supported by extensive data. Yet they did not produce the same answer. Before we reach that disagreement directly, it is important to understand just how much effort went into refining the cosmic ruler. This was not a matter of a few astronomers disagreeing casually. It involved decades of work, thousands of observations, and constant re-evaluation of assumptions. One source of difficulty lies in the fact that the universe is not empty. Matter bends light. Dust absorbs it. Galaxies cluster together under gravity, introducing local motions that can slightly distort redshift measurements. Separating the smooth expansion of space from these local effects requires careful statistical treatment. Another complication is that the expansion rate is not truly constant over time. The Hubble constant describes the expansion rate today, but the universe expanded at different speeds in the past. Matter slowed expansion early on. Later, dark energy caused it to accelerate. Translating observations made at different cosmic epochs into a single present-day number requires a model of how expansion evolved. This means that measuring the expansion rate is not just an observational challenge. It is also a theoretical one. Observations must be interpreted within a framework that describes how the universe behaves over time. In the nearby universe approach, this framework plays a relatively small role. Distances are measured directly. Redshifts are interpreted locally. The expansion rate emerges from data with minimal extrapolation. In the early universe approach, the framework is essential. Observations of ancient light must be translated through a model to predict what the expansion rate should be today. This introduces dependence on assumptions about the universe's contents and behaviour. For a long time, these two approaches were consistent within uncertainties. Differences existed, but they were small enough to be attributed to measurement error. As data quality improved, those uncertainties shrank. Instead of converging, the results drifted apart. At first, this was uncomfortable, but not alarming. Cosmology has seen many apparent discrepancies resolve themselves with better understanding. Astronomers are trained to suspect systematics, subtle biases that affect measurements in ways that are hard to detect. A miscalibrated distance scale, an overlooked effect of dust, a statistical assumption that breaks down at high precision. Teams re-examined their methods, they tested alternative calibrations, they compared independent datasets. The cosmic ruler was scrutinized from every angle. What made the situation increasingly puzzling was that improvements did not erase the discrepancy. Each side became more confident in its result. The error bars became smaller, the disagreement became clearer. This was not a case of one method being sloppy and the other precise. Both were careful, both were internally consistent, both used the same fundamental physics of redshift and light. The ruler itself was not broken. The question was whether it was being applied to the same universe in the same way. There is something quietly profound about this moment in science. For generations, astronomers struggled simply to measure cosmic distances at all. Now they had reached a point where they could measure them well enough to uncover tensions that hint at deeper issues. Precision had become a double-edged sword. From a broader perspective, this is exactly how scientific understanding advances. When measurements are crude, many theories can coexist. As measurements sharpen, some ideas are ruled out. Occasionally, the data challenge the framework itself. The expansion rate of the universe sits at the intersection of observation and theory. It depends on how we read light, how we build distance scales, and how we model cosmic history. A disagreement here does not point to a small oversight. It points to something fundamental. Still, there is no rush to judgment. The universe is under no obligation to match our expectations. It may be that subtle effects remain unaccounted for. It may be that our models, while broadly correct, need refinement. Or it may be that something genuinely new is at play. For now, what matters is that the cosmic ruler exists, and that it has revealed a surprising result. The universe can be measured. Its expansion can be quantified. And when we do so with enough care, the numbers tell a story that is not yet finished. Measuring distance in the universe requires a certain kind of humility. You cannot reach out and mark the space between galaxies. You cannot pace it off or bounce a signal there and back in any practical way. Instead, you have to rely on what the universe offers freely: light, repetition, and consistency. This is where standard candles enter the story, not as poetic objects but as practical tools, quiet benchmarks that allow astronomers to turn faint glows into numbers. The idea behind a standard candle is straightforward. If you know how bright something truly is, and you can measure how bright it appears to be, then the difference between those two tells you how far away it must be. Light spreads out as it travels. Double the distance and the brightness drops by a predictable amount. This relationship is not negotiable. It is built into geometry itself. The challenge, of course, is finding objects whose true brightness you can trust. Most things in the universe are unreliable in this sense. Stars vary in size, temperature, and age. Galaxies contain wildly different numbers of stars and amounts of dust. Even objects that look similar can differ enormously in how much light they produce. Without some internal reference, apparent brightness alone tells you very little. Standard candles are different because they come with a built-in guarantee. Their intrinsic brightness can be determined independently of distance. That makes them cosmic yardsticks, objects that allow astronomers to lay down a scale across space, one step at a time. One of the earliest and most important classes of standard candles comes from a type of star whose behavior is not random at all. Cepheid variable stars brighten and dim in a regular repeating cycle. The key insight, discovered through painstaking observation, is that the period of this cycle is directly related to the star's true luminosity. Slow pulsations mean higher brightness. Faster pulsations mean lower brightness. This relationship was uncovered by Henrietta Leavitt in the early 20th century, while she was studying photographic plates of stars in nearby galaxies. At the time, the significance of her finding was not fully appreciated, yet it would become one of the foundational tools of modern cosmology. Once this relationship was established, Cepheid variables became immensely valuable. Measure how long a Cepheid takes to brighten and dim, and you know how bright it truly is. Compare that to how bright it appears from Earth, and the distance follows. These stars are luminous enough to be seen in nearby galaxies, but not so bright that they dominate their surroundings. They occupy a sweet spot visible across millions of light years, but still common enough to be found in significant numbers. This made them ideal for extending the distance ladder beyond the Milky Way. Still, Cepheids have limits. They cannot be seen at the farthest reaches of the universe. Their light fades into the background long before you reach the most distant galaxies. To push farther, astronomers needed a brighter candle. That candle arrived in the form of stellar explosions, Type 1. As supernovae are among the most luminous events in the universe. For a brief period, a single exploding star can outshine an entire galaxy. What makes these explosions especially useful is their remarkable consistency. They occur when a white dwarf star reaches a critical mass and undergoes a runaway nuclear reaction. Because that critical mass is nearly the same in every case, the resulting explosion has a predictable brightness. This does not mean every Type 1a supernova is identical. There are small variations, but these can be corrected for by studying the shape of the light curve, how quickly the explosion brightens and fades. With these corrections applied, Type 1a supernovae become extraordinarily reliable standard candles. Unlike Cepheids, supernovae can be seen across billions of light years. They allow astronomers to measure distances deep into the universe, far beyond the reach of individual stars. In many ways, they form the backbone of modern distance measurements. The relationship between these different standard candles is crucial. Cepheids are used to measure distances to nearby galaxies. Those distances calibrate the true brightness of supernovae observed in the same galaxies. Once supernova brightness is calibrated, they can be used to measure distances much farther away. This layering is why the distance ladder metaphor matters. Each rung depends on the one below it. If the lower rungs are unstable, the entire structure wobbles. If they are secure, the ladder extends confidently outward. Astronomers are acutely aware of how sensitive this process is. A small error in the calibration of Cepheids can propagate into a larger error in supernova distances. That, in turn, affects measurements of the universe's expansion rate. For this reason, enormous effort has gone into refining these calibrations. Space-based telescopes have played a critical role here. Observing Cepheids from above Earth's atmosphere reduces distortion and allows for more precise measurements of brightness and period. This has helped tighten uncertainties and improve confidence in distance estimates. Even so, complications remain. Dust is one of the most persistent challenges. Dust between stars and galaxies absorbs and scatters light, making objects appear dimmer than they truly are. If not accounted for correctly, this can make distances seem larger than they are. Astronomers correct for dust using colour information and models of how dust behaves, but these corrections are never perfect. Another issue is environment. Cepheids in different galaxies may differ slightly in composition. Supernovae occurring in different stellar populations may have subtly different properties. Each of these factors can introduce small biases that only become apparent at high precision. For a long time, these issues were thought to be under control. Independent teams using different datasets and methods arrived at similar expansion rates when relying on standard candles. The consistency was reassuring. It suggested that the cosmic ruler, while complex, was fundamentally sound. As measurements improved further, however, something unexpected happened. The distances derived from standard candles, when paired with redshift measurements, consistently implied a faster expansion rate than that inferred from observations of the early universe. This was not a single anomalous result. It appeared across different studies, using different telescopes, different samples of stars and supernovae, and different analysis techniques. The agreement among local measurements was strong. The disagreement with early universe predictions was persistent. This placed standard candles at the centre of a growing puzzle. If the nearby universe was expanding at one rate, and the early universe implied a different rate, then something had to give. Either the standard candles were subtly misleading, or the interpretation of early universe data was incomplete, or the universe itself was behaving in a way not fully captured by existing models. From the perspective of the standard candle approach, confidence was high. Cepheid physics is well understood, supernova explosions are studied in detail, calibration techniques are tested repeatedly. While no measurement is perfect, the level of agreement within the local universe is difficult to dismiss. Yet science does not operate on confidence alone. It operates on consistency across methods. This is where the tension becomes interesting rather than troubling. Standard candles are not isolated measurements. They're embedded within a network of observations that include redshift surveys, galaxy clustering, and background radiation. When one part of that network disagrees with another, it signals an opportunity to learn. It is also worth remembering that standard candles do not measure expansion directly. They measure distance. Expansion enters when distance is compared to redshift. This means that any systematic issue affecting either side of that comparison can influence the result. Astronomers have explored numerous possibilities. Could Cepheids be affected by unseen companions? Could supernovae evolve subtly over cosmic time? Could dust behave differently in distant galaxies? Each idea has been investigated carefully. So far, none has resolved the discrepancy fully. This does not mean the standard candles are wrong. It means they are precise enough to raise questions that were invisible before. In that sense, they are doing exactly what good scientific tools should do. They are revealing the limits of our current understanding. As a listener, you do not need to hold all these details at once. The important idea is simple. The universe provides certain objects whose behaviour allows us to measure distance reliably. These objects form the backbone of one way of determining how fast the universe is expanding. That way produces a clear, consistent answer. The surprise is that another equally careful method produces a different one. Standard candles flicker steadily, indifferent to the debates they inspire. They pulse and explode according to the same physical laws they always have. The light they emit travels faithfully across space, carrying information we are still learning how to interpret. Long before the universe could be measured in billions of light years, it had to be measured in something much smaller and far more familiar. Before expansion rates, background radiation, or competing numbers entered the conversation, astronomers faced a simpler but more stubborn problem. They needed to know how far away anything was at all. Without distance, motion had no scale, brightness had no meaning, and the night sky remained a flat map with no depth. The first true steps outward did not begin with galaxies or explosions or ancient light. They began with stars that refused to shine steadily. Cepheid variable stars do not behave like most stars. Instead of glowing at a constant brightness, they rhythmically brighten and fade over and over again, with periods ranging from a few days to several weeks. This pulsing is not random or chaotic. It follows a precise physical process tied to the structure of the star itself. Layers within the star expand and contract, trapping and releasing energy in a repeating cycle that can continue for millions of years. At first, these stars were curiosities, catalogued for their odd behaviour, but not yet understood as tools. Their importance only became clear once astronomers noticed something remarkable. The rhythm of a Cepheid's pulse was directly linked to how much light it truly produced. Slow, long pulses meant a very luminous star. Faster pulses meant a dimmer one. This relationship was stable, repeatable, and universal. Once that connection was recognized, Cepheids transformed astronomy. For the first time, astronomers had access to stars whose true brightness could be determined without knowing their distance beforehand. Measure the period of the pulse, and the intrinsic luminosity follows. Compare that intrinsic brightness to how bright the star appears from Earth, and distance emerges naturally. This was revolutionary not because it was flashy, but because it was reliable. Unlike many astronomical techniques, Cepheid distance measurement did not depend on complex modelling of galaxies or assumptions about cosmic history. It relied on stellar physics that could be tested locally. Cepheids in our own galaxy could be studied in detail. Their distances could be verified using geometric methods. Once calibrated nearby, the same relationship could be applied to Cepheids in other galaxies. This calibration step was crucial. Astronomers first used parallax to measure distances to the nearest Cepheids. Parallax, the apparent shift in a star's position as Earth orbits the Sun, is a purely geometric effect. It does not depend on brightness, models, or assumptions about stellar behaviour. It is as close to a gold standard as astronomy can achieve. With those nearby distances in hand, the period-luminosity relationship could be anchored securely. Cepheids became the first rung of a cosmic distance ladder that could extend far beyond the Milky Way. When astronomers began identifying Cepheids in nearby galaxies, everything changed. Those faint points of light were no longer just stars, they were mile markers in space. This is how the universe first acquired depth. Before Cepheids, galaxies could be ranked by apparent size or brightness, but those rankings were ambiguous. A small nearby galaxy could appear similar to a massive distant one. Cepheids broke that ambiguity. They provided absolute distances, revealing that some objects lay far beyond the Milky Way, while others were much closer than assumed. This was the method that allowed astronomers to establish that spiral nebulae were actually entire galaxies. It was the first time humanity could confidently say, this object is millions of light years away, and mean it numerically. Once distances to galaxies were known, redshift measurements gained context. A galaxy's spectral shift could now be paired with a distance that was not guessed but calculated. Plot enough of these pairs, and the expansion of the universe revealed itself. This is why Cepheids sit at the foundation of expansion measurements. They are not glamorous compared to supernovae or background radiation, but they are indispensable. Without them, the nearby universe remains uncalibrated, and every higher level measurement floats without anchor. Still, Cepheids are not perfect. They exist only in certain types of galaxies, those with ongoing star formation. They are bright, but not infinitely so. Beyond a certain distance, even the largest telescopes struggle to isolate them from surrounding starlight. Crowding becomes an issue, dust becomes an issue, resolution becomes an issue. Astronomers have spent decades addressing these challenges. Observing Cepheids from space avoids atmospheric distortion. Careful statistical methods correct for blending with nearby stars. Observations in infrared wavelengths reduce the impact of dust. Each refinement sharpens the ladder. What makes Cepheids especially important in the current context is not just that they provide distances, but that they link different measurement regimes together. Cepheids connect geometric measurements in our local neighbourhood to supernova measurements in distant galaxies. They are the hinge on which the entire local distance scale turns. If Cepheids are miscalibrated, everything above them shifts. For this reason, Cepheid studies are among the most scrutinized in astronomy. Independent teams analyze the same stars using different techniques. Distances are cross-checked with alternative methods where possible. Systematic uncertainties are catalogued exhaustively. Despite this scrutiny, Cepheid-based distances have proven remarkably stable. As measurements improved, the distances derived from Cepheids did not wander wildly. They converged. Different groups, using different data sets and methods, arrived at closely matching results. This consistency is one reason astronomers place so much confidence in the local distance ladder. And it is precisely this confidence that makes the present disagreement so striking. When Cepheid-calibrated distances are used to measure the expansion rate of the nearby universe, the resulting number is consistently higher than the value inferred from early universe observations. This is not a marginal effect. It persists across data sets and refinements. If Cepheids were unreliable, the problem would be easier. But their behavior is well understood, their calibration repeatedly tested, and their results internally consistent. This has led astronomers to ask uncomfortable but necessary questions. Could Cepheids behave differently in other galaxies than they do locally? Could metallicity, the abundance of heavier elements, subtly affect their brightness? Could unresolved companions skew measurements? Each possibility has been examined carefully. Metallicity does have an effect, but it is small and already accounted for. Companion stars can introduce bias, but corrections reduce this impact significantly. None of these effects appear large enough to explain the full discrepancy. This does not mean Cepheids are beyond question. It means that questioning them has so far reinforced their reliability rather than undermined it. Another important point is that Cepheids do not operate in isolation. They are part of a chain. Parallax calibrates Cepheids. Cepheids calibrate supernovae. Supernovae measure expansion. If something were fundamentally wrong with Cepheids, inconsistencies would appear elsewhere in the ladder as well. So far, they have not. This is why the current tension cannot be dismissed as a simple measurement error. The first rung of the ladder appears solid. The higher rungs are independently strong. Yet when the ladder is compared to a completely different approach that does not rely on stars at all, the numbers disagree. In a way, Cepheids have done their job too well. By enabling precise local measurements, they have exposed a mismatch that cruder tools would have hidden. There is also something quietly human about this part of the story. Cepheids pulse patiently, indifferent to cosmological debates. They have been doing so long before humans existed and will continue long after. Their regularity is not for us, but we have learned to use it. As listeners, it can be comforting to think of these stars as steady companions in an otherwise confusing universe. They flicker predictably, providing reference points in a cosmos that is otherwise difficult to measure. Yet even these steady beacons cannot tell the whole story alone. Cepheids measure distances out to tens of millions of light years. That is vast by human standards, but small compared to the observable universe. Beyond that range, astronomers must rely on brighter indicators, objects that can be seen across much greater distances. Those brighter indicators depend on Cepheids for calibration, but they introduce new physics, new uncertainties, and new opportunities for discovery. By the time astronomers reach the limits of what individual stars can tell them, the universe does not politely stop offering clues. Instead, it provides something far more dramatic. Stars that do not merely flicker or pulse, but end their lives in explosions so bright they briefly overwhelm the darkness around them. These events are rare, violent, and fleeting, yet they have become some of the most important tools for measuring the universe on its larger scales. Supernovae enter the story not as accidents, but as necessities. Cepheid stars allow astronomers to measure distances to nearby galaxies with confidence, but beyond that range, their light simply fades into the background. Even the most powerful telescopes struggle to isolate individual stars at extreme distances. To continue outward, something brighter is required, something that can be seen across hundreds of millions, even billions of light years. Supernovae provide exactly that. A supernova is not a single phenomenon, but a category of stellar death, encompassing several different physical processes. Massive stars can collapse under their own gravity and rebound violently, tearing themselves apart. Other stars meet their end in quieter but equally destructive ways, accumulating matter until a critical threshold is crossed. Among these various endings, one type stands out for its usefulness as a cosmic measuring tool: Type 1. A supernovae occur when a dense stellar remnant, known as a white dwarf, gains too much mass. This can happen through interaction with a companion star or the merger of two white dwarfs. Once the mass crosses a precise physical limit, the star can no longer support itself. A runaway nuclear reaction ignites, and the star detonates. What makes this process remarkable is its consistency. Because the critical mass at which the explosion occurs is nearly the same every time, the resulting explosion releases a predictable amount of energy. That energy translates into a characteristic brightness. While individual events vary slightly, those variations follow patterns that can be measured and corrected for. Once those corrections are applied, Type 1a supernovae behave as reliable standard candles. For a brief period, often a few weeks, a single supernova can shine as brightly as the billions of stars in its host galaxy combined. This makes it visible across vast distances, far beyond the reach of Cepheids. Where Cepheids provide the first rung of the distance ladder, supernovae extend it outward dramatically. The process works like this. Astronomers first observe Cepheid stars in a nearby galaxy. Though Cepheids establish the distance to that galaxy with high confidence, if a Type 1a supernova occurs in the same galaxy, its apparent brightness can be compared to the known distance. That allows astronomers to determine the supernova's true brightness. Once that true brightness is calibrated, Type 1a supernovae observed in much more distant galaxies can be used to measure distances far beyond the local universe. The ladder continues upward, one explosion at a time. This handoff between Cepheids and supernovae is one of the most carefully studied transitions in cosmology. It has been refined repeatedly, tested across different environments, and scrutinized for hidden biases. The reason is simple. Supernovae sit at the heart of local expansion measurements. If something is wrong here, the consequences ripple outward. For many years, this method performed beautifully. When distances derived from supernovae were compared to redshift measurements, the relationship was clear and consistent. Galaxies farther away showed larger redshifts, indicating faster recessional motion. The slope of that relationship yielded an expansion rate that seemed stable and repeatable. Then something unexpected happened. As more supernovae were observed at greater distances, astronomers noticed not just expansion, but acceleration. Distant supernovae appeared dimmer than expected, suggesting that the universe's expansion had been speeding up over time. This discovery led to the idea of dark energy, a mysterious component that drives accelerated expansion. This result was profound, but it also reinforced confidence in supernova measurements. Independent teams using different samples and methods arrived at the same conclusion. The supernova data were not chaotic or contradictory. They told a coherent story. That coherence is important when considering the present tension. When supernova calibrated distances are combined with Cepheid measurements and redshift data, the expansion rate inferred for the nearby universe consistently comes out higher than the value inferred from early universe observations. This result is not fragile. It does not depend on a single dataset or a single analysis choice. It emerges repeatedly. To challenge it, astronomers have examined supernovae from every angle. They have asked whether supernovae in distant galaxies behave differently than those nearby. Could stellar populations evolve in ways that subtly affect explosion brightness? Could dust in distant galaxies dim light in unexpected ways? Could selection effects bias which supernovae are detected? Each of these questions has been investigated carefully. Supernova-like curves are studied in detail, not just peak brightness, but the entire rise and fall of the explosion. These curves encode information about the physics of the event and allow corrections that standardize brightness. Comparisons across redshift show no evidence of large unaccounted-for evolution. Dust is a persistent concern, but multi-wavelength observations help disentangle dust effects from intrinsic brightness. Statistical methods account for selection bias, ensuring that brighter, easier-to-detect supernovae do not skew results artificially. While small uncertainties remain, none appear large enough to explain the full discrepancy. This is what makes supernovae so central to the current puzzle. They are not new, poorly understood tools. They are mature, well-tested instruments of measurement. Their consistency across space and time is precisely why they revealed cosmic acceleration in the first place. If supernovae were fundamentally unreliable, the discovery of acceleration itself would be suspect. Yet that discovery has withstood decades of scrutiny. There is also an important conceptual point here. Supernovae do not measure expansion at a single moment. They sample it across a range of distances and times. Nearby supernovae reflect recent expansion. Distant ones probe earlier epochs. When analysed together, they trace how expansion has evolved. In the local universe, where supernovae overlap with Cepheid calibrated distances, the expansion rate they imply is clear. It is faster than what early universe models predict. This raises an intriguing possibility. Perhaps the universe's expansion history is more complex than currently assumed. Perhaps something subtle changes between early and late times. Supernovae, by bridging those epochs, may be highlighting that transition. It is also worth remembering that supernovae are independent of many assumptions that affect other measurements. They do not rely on early universe physics. They do not depend on conditions shortly after the Big Bang. They measure distance and redshift directly, here and now, using objects that exist in the present universe. That immediacy gives their results a particular weight. From a broad perspective, there is something fitting about this. The most violent events in the universe, the deaths of stars, have become tools for understanding its larger scale behaviour. Destruction, in this case, illuminates structure. As listeners, it is not necessary to track every correction or statistical nuance. The essential idea is simpler. Supernovae are extraordinarily bright, remarkably consistent explosions that allow astronomers to measure distances across much of the observable universe. When those distances are compared to redshift, they reveal how fast the universe is expanding nearby. That speed does not match what we infer from looking deep into the past. Supernovae do not resolve the disagreement, they sharpen it. They stand between Cepheid stars and ancient background light, connecting the local universe to cosmic history, and in doing so, they insist that the numbers derived from nearby measurements are not easily dismissed. Does not describe a particle, a force, or does not describe a particle, a force, or a specific object. Instead, it summarizes the present behavior of the entire universe. It tells us, in compact form, how quickly space itself is expanding right now. At first glance, that might sound like an abstract curiosity, the sort of thing that matters only to specialists. But the consequences of this number extend much farther than its definition suggests. The value assigned to the Hubble constant influences estimates of the universe's age, the size of the observable cosmos, the growth of structure, and the balance between matter, radiation, and dark energy. Change the number slightly, and the universe you infer changes with it. This is why disagreement over the Hubble constant is not a technical footnote. It is a signal that something important may be unresolved. To understand why this number carries such weight, it helps to return briefly to what it represents. The Hubble constant links distance and recessional speed. For every additional megaparsec of distance between us and a galaxy, there is an additional amount of recessional velocity caused by cosmic expansion. Multiply the distance by the Hubble constant, and you get the expected expansion-related speed. Despite the word constant, this value is not fixed across cosmic time. The universe expanded at different rates in the past. Matter slowed expansion early on. Dark energy accelerated it later. The Hubble constant refers specifically to the expansion rate today at the current age of the universe. This distinction matters because different measurement methods do not all sample the same epochs. Some measure expansion directly in the nearby universe. Others infer it indirectly by modelling how the universe evolved from its earliest observable state. In principle, both approaches should converge on the same present-day value. In practice, they do not. When astronomers using Cepheids stars and supernovae measure the Hubble constant locally, they obtain a value that suggests a relatively fast expansion today. When astronomers use early universe observations and project forward using well-tested models, they obtain a lower value, implying slower expansion. The difference is not subtle anymore. It exceeds what can reasonably be attributed to random error, and because both approaches are internally consistent, the disagreement cannot be dismissed casually. This has led to a great deal of careful thinking about what the Hubble constant actually encodes. One immediate consequence of its value is the inferred age of the universe. A faster expansion rate today generally implies a younger universe, all else being equal. A slower expansion suggests more time has passed since the universe was much denser. While this relationship is not perfectly linear, the dependence is strong enough that differing Hubble constant values lead to age estimates that differ by hundreds of millions of years. Those differences matter because they must be consistent with independent age estimates. The oldest stars in the Milky Way, for example, provide a lower bound on the universe's age. Any cosmological model must allow enough time for those stars to form and evolve. If the Hubble constant were too large, the implied universe could be younger than its own contents, an obvious problem. Modern measurements avoid that extreme conflict, but the margin is not large. A higher Hubble constant pushes the universe toward the younger end of what stellar ages allow. A lower value provides more breathing room. The Hubble constant also affects the inferred size of the observable universe. The faster space expands, the farther light has travelled since the beginning. This influences how much of the universe we can, in principle, observe. It shapes estimates of cosmic horizons and the scale of large structures. Beyond size and age, the Hubble constant plays a role in understanding how galaxies and clusters formed. Structure formation depends on how quickly matter could clump together under gravity before expansion pulled things apart. A faster expansion rate today suggests a different balance between gravity and expansion over time, which in turn affects how structures grow. Because of these connections, the Hubble constant is woven deeply into cosmological models. It is not a standalone parameter that can be adjusted freely without consequences. Change it, and other pieces must adjust as well. This interconnectedness is part of what makes the current tension so informative. It is not just that two numbers differ, it is that each number fits comfortably within a different but internally coherent picture of the universe. On the local side, the picture is grounded in direct measurement. Cepheids pulse, supernovae explode, distances are calculated, redshifts are measured. The expansion rate emerges from data that describe the nearby universe as it exists now. On the early universe side, the picture is grounded in physics that has been tested repeatedly in other contexts. The behaviour of matter and radiation in the early universe is well understood. The equations that describe how small fluctuations grow into large structures are robust. When these are applied to early universe observations, they predict a specific expansion history, including a present-day Hubble constant. Neither picture is ad hoc, neither is obviously flawed. This is why the Hubble constant has become a focal point rather than a peripheral detail. It sits at the intersection of observation and theory, and at that intersection, something does not line up. It is tempting to think of this as a failure of measurement, but that framing is misleading. Measurements are doing exactly what they should do. They are precise enough to reveal inconsistencies that were previously hidden. The discomfort arises not because the data are unreliable, but because they are reliable enough to disagree meaningfully. Another way to think about the Hubble constant is as a diagnostic tool. It tests whether our model of the universe, which includes dark matter, dark energy, and known forms of radiation, is complete. If all components are correctly identified and described, then independent measurements should converge. If they do not, then either something is missing or something is being misinterpreted. This does not mean the model is wrong in a dramatic sense. It may be incomplete in subtle ways, a small additional component, a slight modification to how energy behaves, or an overlooked interaction could reconcile the numbers. Alternatively, the resolution may lie in measurement after all, but at a deeper level than initially expected. Perhaps there is a systematic effect that affects local distance measurements in a correlated way. Perhaps early universe interpretations rely on an assumption that needs refinement. The challenge is that many obvious possibilities have already been examined and found wanting. Astronomers have varied analysis techniques. They have used different samples, they have tested alternative calibrations, they have looked for environmental effects. None of these efforts have erased the discrepancy. As a result, the Hubble constant has taken on a role it was never intended to have. It has become a probe of new physics. This does not mean that new physics is guaranteed. Science is cautious by design. Extraordinary claims require extraordinary evidence. At present, the evidence says that there is a persistent, statistically significant tension. Interpreting that tension is an ongoing process. It is also worth noting that the Hubble constant is not the only parameter in cosmology. Many others describe the universe's contents and behaviour. What makes the Hubble constant special is that it can be measured in conceptually simple ways. Distance and speed are intuitive quantities. When disagreement arises here, it feels especially striking. It may help to think of the Hubble constant as a summary of everything that came before. Cepheids establish distances, supernovae extend those distances, redshift measures motion, combine them, and you get a number. That number, in turn, must align with what we infer from the universe's earliest light. When it does not, the discrepancy does not live in isolation. It echoes backward through the entire measurement chain and forward into theoretical interpretation. This is why discussions of the Hubble constant are rarely just about the number itself. They quickly branch into questions about dark energy, the nature of space-time, and the possibility of unknown components influencing cosmic expansion. Still, there is no sense of crisis here. The universe is not broken. Our understanding is simply being tested at a finer level than before. Historically, moments like this have often preceded major advances. Small discrepancies in planetary motion led to new theories of gravity. Unexpected spectral lines led to quantum mechanics. In each case, the universe was behaving consistently. It was our descriptions that needed adjustment. Whether the Hubble constant tension will lead to a similar shift remains to be seen. It may resolve quietly through improved measurements. It may point toward new physics. Or it may require a combination of both. For now, the number sits uneasily between two methods, carrying implications far beyond its modest appearance. It tells us that measuring the universe is not just about accumulating data, but about ensuring that different windows onto reality truly describe the same thing. Long before there were stars to flicker, galaxies to drift apart, or supernovae to briefly light up the darkness, the universe existed in a very different state. It was hot, dense, and opaque, filled with a thick fog of particles and radiation interacting constantly. Light could not travel freely. Space, as we would recognize it, was crowded and restless. Yet from that distant era, something remains, a quiet signal that still fills the universe today and carries with it a detailed record of how everything once behaved. This signal is known as the cosmic microwave background, often shortened to CMB. It is not a picture in the ordinary sense, and it is not light you can see with your eyes. It is a faint bath of microwave radiation that arrives from every direction, nearly uniform, almost perfectly smooth, and extraordinarily informative. The existence of this background light was predicted before it was discovered. It followed naturally from the idea that the universe had once been much hotter and denser than it is now. If that were true, then as the universe expanded and cooled, there would come a moment when matter and radiation stopped interacting constantly. At that point, light would be free to travel without being scattered. That light would continue moving through space ever since, stretched to longer wavelengths by cosmic expansion. Until today, it appears as microwaves rather than visible light. When this background radiation was finally detected, it confirmed that the universe had indeed passed through such a hot, dense phase. But confirmation was only the beginning. As instruments improved, astronomers realized that the cosmic microwave background was not perfectly uniform. Tiny variations in temperature and density were present, differences of only a few parts in 100,000. Those variations turned out to be the seeds of everything that followed. Galaxies, clusters, and large-scale structure all grew from those initial irregularities. The power of the cosmic microwave background lies in the fact that it captures the universe at a very specific moment in time. Roughly 380,000 years after the beginning of cosmic expansion, conditions changed enough for light to decouple from matter. Before that moment, photons were constantly scattered by charged particles. After it, they streamed freely. The CMB is a snapshot of that transition. Because the physics of this era is relatively simple and well understood, the patterns in the CMB can be modelled with remarkable precision. Matter, radiation and gravity interacted in ways described by equations that have been tested extensively. By analysing the size, distribution and amplitude of the tiny temperature fluctuations in the CMB, scientists can infer the contents of the universe and how it evolved. This includes the density of ordinary matter, the amount of dark matter, the influence of radiation, and the role of dark energy. Importantly for our story, it also includes information about the expansion rate of the universe. The cosmic microwave background does not measure the Hubble constant directly. Instead, it provides a detailed account of conditions in the early universe. From that account, scientists use a model of cosmic evolution to calculate what the expansion rate should be today. This distinction is crucial. When astronomers analyse the CMB, they are not measuring nearby galaxies or stars. They are reading a relic from a time long before any of those objects existed. The expansion rate inferred from the CMB is therefore indirect. It depends on the assumption that the model used to connect early conditions to the present is complete and correct. For many years, this approach worked exceptionally well. The model used, often referred to as the standard cosmological model, successfully explains a wide range of observations. It predicts the relative abundances of elements formed early in cosmic history. It accounts for the large-scale distribution of galaxies. It describes how structures grow over time, and when applied to the cosmic microwave background, it produces predictions that match observations with astonishing accuracy. Within this framework, the expansion rate inferred from the CMB is lower than the value measured locally using Cepheids and Supernovae. The difference is not enormous, but it is persistent, and because the CMB measurements are extremely precise, the uncertainty on that inferred value is small. This is what gives the disagreement its weight. The cosmic microwave background is often described as one of the cleanest datasets in cosmology. The radiation has travelled through space largely unimpeded. It is not affected by dust in the same way visible light is. It does not depend on the complex physics of stars or explosions. It reflects conditions from a time when the universe was simpler. Because of this, many scientists place great trust in what the CMB reveals. The analysis process is intricate but conceptually clear. Temperature variations across the sky are mapped with exquisite detail. The angular size of these variations encodes information about the geometry of the universe. Their relative heights and spacing depend on how matter and radiation interacted before recombination. By fitting models to these patterns, cosmologists extract a set of parameters that describe the universe as a whole. One of those parameters is the Hubble constant, not measured directly but inferred. When this inference consistently yields a value lower than local measurements, the question becomes unavoidable. Is the model missing something? Or are the local measurements subtly biased in a way not yet understood? From the perspective of the early universe, the logic is compelling. Given the observed CMB patterns and a well-tested physical framework, the expansion rate today should have a specific value. Deviating from that value would require altering the model in some way. Such alterations are not impossible, but they are constrained. Any change must preserve the model's success in explaining everything else the CMB gets right. This is a tall order. One possibility is that additional components existed in the early universe, altering expansion before recombination. Extra forms of radiation, for example, could change how quickly the universe expanded at early times, leading to a different inferred Hubble constant today. These ideas are explored carefully, but they must fit within tight observational limits. Another possibility is that dark energy behaves differently than assumed. In the standard picture, dark energy becomes important only relatively recently. If its behavior changed over time, it could affect the relationship between early and late expansion. Again, such changes must be subtle enough not to disrupt other observations. There is also the possibility that gravity itself behaves slightly differently on cosmic scales. Modifications to general relativity have been proposed, but they are heavily constrained by data from many sources. Each of these ideas represents a way to reconcile the CMB inferred expansion rate with local measurements. None has yet provided a fully satisfactory solution. What makes the cosmic microwave background especially intriguing in this context is its internal consistency. The same data set that implies a lower Hubble constant also matches a wide array of other observations. This coherence makes it difficult to dismiss the result as a fluke or artifact. At the same time, the CMB does not exist in isolation. Its interpretation depends on assumptions. While those assumptions are well motivated and extensively tested, they are still assumptions. If something about the universe's contents or behavior has been overlooked, the inferred expansion rate could shift. This is the delicate balance at the heart of the current tension. On one side, local measurements tell us how the universe appears to be expanding now, based on direct observation of stars and galaxies. On the other side, the cosmic microwave background tells us how the universe behaved when it was young, and, through a model, how that behavior should connect to the present. Both stories are internally consistent, both are supported by strong evidence. And yet, they do not quite tell the same story about how fast expansion is happening today. From a broader perspective, this is not a failure. It is a moment of opportunity. The CMB gives us a view of the universe in its infancy. Local measurements give us a view of it in maturity. If those views disagree, then the transition between them holds valuable information. It may be that the universe's expansion history includes features we do not yet fully understand. It may be that subtle physical effects become important only at certain times. Or it may be that the resolution lies in refining measurements further. It is worth emphasizing that the cosmic microwave background is not mysterious in the sense of being vague or poorly understood. It is one of the most precisely measured phenomena in science. Its patterns have been mapped, analyzed, and reanalyzed countless times. The disagreement it reveals is not born of ignorance, but of precision. As we sit with this idea, there is no need to resolve it immediately. The universe is under no pressure to explain itself quickly. It has left us a detailed record of its early state, written in faint microwaves that fill all of space. We are still learning how to read that record fully. At some point, comparison becomes unavoidable. Once measurements grow precise enough and methods mature enough, the numbers they produce have to be placed side by side. That moment arrived quietly in cosmology, not with an announcement, but with spreadsheets, plots, and tables that stubbornly refused to line up. On one side sat the nearby universe, distances measured step by step, from parallax to Cepheid stars to supernovae. Redshifts recorded carefully, expansion inferred directly, here and now, from objects that exist in the present cosmic neighborhood. On the other side stood the early universe, patterns frozen into ancient radiation, decoded through well-tested physics, projected forward across billions of years to predict how fast expansion should be today. When those two approaches were first compared seriously, the expectation was simple. They might differ slightly, but as uncertainty shrank, they would converge. That is what science trains us to expect. Independent methods grounded in the same underlying reality should eventually agree. They did not. At first, the disagreement was easy to dismiss. Early measurements of the expansion rate had large error bars. Different values overlapped comfortably. Any apparent difference could be blamed on limited data or incomplete calibration. No one was alarmed. But as the years passed, the situation changed. Observations improved, telescopes became more sensitive, analysis techniques grew more sophisticated, error bars tightened. And instead of drifting toward one another, the two values began to separate. The local measurements based on stars and supernovae consistently pointed to a faster expansion rate. The early universe measurements based on the cosmic microwave background and a standard cosmological model consistently pointed to a slower one. The gap between them grew clearer, not because the numbers moved dramatically, but because confidence in each increased. This is the moment when a discrepancy turns into a tension. To understand why this was so unsettling, it helps to look carefully at how different these two methods are. They do not share the same assumptions. They do not rely on the same physical processes. They do not even observe the universe at the same stage of its life. The local method is almost stubbornly concrete. It starts nearby, with stars whose behavior can be studied in detail. It builds outward in careful steps. Each distance is tied to a physical object that can be observed repeatedly. Redshift measurements are paired with these distances to infer expansion. The logic is straightforward, even if the execution is demanding. The early universe method, by contrast, is global and indirect. It looks at the universe when it was extremely young, long before stars or galaxies existed. It relies on a model that describes how the universe evolves from that early state to the present. Within that model, the expansion rate today is not measured, but predicted. This difference matters because it means the two methods are vulnerable to different kinds of error. If something were wrong with the local measurements, it would likely involve astrophysical complications, dust, stellar evolution, calibration issues, selection bias. These are messy, real-world problems, but they are also familiar. Astronomers know how to look for them, test for them, and correct for them. If something were wrong with the early universe inference, it would point towards something deeper. Either the model used to describe cosmic evolution is incomplete, or some physical component has been overlooked. This is not impossible, but it carries broader implications. For a long time, most researchers expected the resolution to come from the local side. That is not a criticism of the work, but a reflection of how science usually proceeds. Complex layered measurement chains are often where subtle biases hide. The early universe model, by contrast, had already survived decades of testing across many independent observations. So astronomers went looking for problems in the local ladder. They re-examined parallax measurements. They improved distance calibrations using space-based observatories. They compared Cepheids in different environments. They refined corrections for dust and crowding. They tested whether supernovae behave differently in different kinds of galaxies. Each investigation tightened the methodology. Each reduced uncertainty. And with each refinement, the local expansion rate remained stubbornly high. At the same time, researchers scrutinized the early universe side just as carefully. They checked instrument calibrations. They tested alternative data processing pipelines. They explored how sensitive the inferred expansion rate was to different assumptions within the model. The result was similar. The early universe value remained stable. This is the heart of the problem. The disagreement does not arise because one method is sloppy and the other precise. It arises because both are precise, and they disagree anyway. To put it another way, the universe seems to be telling us two different things depending on how and when we listen. When we listen to nearby stars and galaxies, the universe says it is expanding at one rate. When we listen to the faint whisper of its earliest light, it says something slightly different. Neither statement appears to be wrong on its own. This has forced cosmologists into an uncomfortable position. They must either find a hidden flaw that has eluded years of scrutiny, or accept that the standard picture of the universe may be missing a piece. It is important to stress that the difference between the two values is not enormous. We are not talking about a universe expanding twice as fast as expected or half as fast. The discrepancy is on the order of 10%. In everyday contexts, that might seem trivial. In cosmology, it is not. Modern measurements are precise enough that a 10% difference is significant. It exceeds the combined uncertainties of the methods involved. It persists across independent datasets. It refuses to average away. This persistence is what gives the tension its name. Another reason the disagreement matters is that the two methods are not redundant. They complement each other. One probes the universe as it is now. The other probes it as it was then. Together, they should form a coherent narrative of cosmic history. When they do not, the narrative becomes incomplete. There is also a psychological element to this story. Scientists are trained to distrust unexpected results. When a discrepancy appears, the first instinct is to doubt the measurement, not the theory. When repeated checks fail to find an error, the discomfort grows. The Hubble tension has now passed that threshold. It is no longer a curiosity discussed in passing. It has become a central topic in cosmology, precisely because it has not gone away. Various proposals have been put forward to explain it. Some suggest that the local universe might be slightly unusual, perhaps influenced by large-scale structures that bias measurements. If our cosmic neighbourhood were atypical, local expansion might appear faster than average. This idea has been tested using galaxy surveys and simulations. So far, it does not seem sufficient. Others suggest that the early universe might have contained additional components that affected expansion before the cosmic microwave background was released. Extra radiation, new particles, or early forms of dark energy could shift the inferred expansion rate. These ideas are intriguing, but they must fit within tight constraints imposed by other observations. There are also proposals that modify gravity itself. Small deviations from general relativity on cosmic scales could alter expansion history. Such modifications are difficult to construct without conflicting with well-tested predictions elsewhere, but they remain an active area of research. What all these ideas have in common is that they attempt to reconcile two sets of data that are individually robust. This is an important point to hold on to. The tension does not imply that cosmology is broken. It implies that cosmology has reached a level of precision where its assumptions are being tested in new ways. Historically, this is often when progress accelerates. It is also worth noting what the tension does not mean. It does not mean that expansion is illusory. It does not mean that the universe behaves erratically. It does not mean that measurements are arbitrary. The universe is expanding. That fact is beyond doubt. The question is how fast, and whether that speed has been interpreted consistently across cosmic time. From a listener's perspective, it can be reassuring to remember that disagreement in science is not a failure. It is a diagnostic. When different approaches disagree, it tells us where to look more closely. In this case, it tells us to examine the bridge between early and late cosmic history. If the universe's expansion history were perfectly smooth and fully captured by current models, the two methods should agree. If they do not, then either the bridge is incomplete, or the measurements on one side are skewed in ways we have not yet identified. Another way to frame the issue is to think about clocks. Local measurements use clocks embedded in stars and explosions, processes that unfold over millions or billions of years but can be observed directly. Early universe measurements use a cosmic clock encoded in radiation patterns, frozen at a particular moment and read through theory. Both clocks tick according to the laws of physics. If they disagree about how much time has passed, then either one clock is misread or something has altered the ticking along the way. This analogy is imperfect, but it captures the intuition. The disagreement is not about whether time passes, but about how it is counted. As the field has wrestled with this problem, the tone has remained cautious. No consensus has emerged about the correct explanation. Papers propose possibilities, test them, discard them, refine them. The process is ongoing. What has changed is that the tension is now taken seriously as a feature of the data, not a nuisance to be ignored. This seriousness has also influenced how new observations are planned. Upcoming surveys, new telescopes, and alternative measurement techniques are being designed with the explicit goal of probing this discrepancy from new angles. The hope is not just to measure the expansion rate again, but to measure it differently. Different traces, different physics, different systematics. That brings us to a natural pause in the story. We have two methods, we have two answers. We have ruled out many simple explanations. What remains is a puzzle that sits at the boundary of observation and theory. The universe has not changed its behaviour. Our descriptions of it are simply being refined to the point where subtle mismatches can no longer be smoothed over. Rather than announcing itself loudly, the problem arrived as a quiet insistence. The numbers did not clash dramatically. They did not overturn tables or invalidate decades of work overnight. They simply refused to agree, and they kept refusing, no matter how carefully they were asked. Over time, that refusal earned a name, not because it was theatrical, but because it persisted. The Hubble tension. Calling it a tension was deliberate. In science, words matter. A crisis suggests collapse. An anomaly suggests a mistake. A tension suggests something pulled in two directions at once, stretched but not broken. That is exactly how this situation feels from within the field. Two careful, independent methods are pulling on the same underlying reality, and the stretch between them is no longer ignorable. The question that naturally follows is deceptively simple. Is this tension a whisper, a small statistical oddity that will fade as measurements improve, or is it a warning, an early sign that something fundamental is missing from our picture of the universe? To answer that, it helps to step back from the numbers themselves and think about how science usually treats disagreement. Most discrepancies die young. A new dataset appears inconsistent with previous results. Researchers recheck calibrations, correct an error, refine an assumption, and the problem dissolves. This happens so often that it is almost routine. Experienced scientists expect it. Improved. Their internal consistency strengthened. As early universe measurements improved, their internal consistency strengthened as well. The gap between them did not close, it became sharper. At this point, the tension has survived enough scrutiny that it can no longer be dismissed as a transient artifact of incomplete data. That survival alone does not guarantee profound consequences. Nature is under no obligation to reveal new physics every time we refine a measurement. Sometimes the resolution really does lie in a subtle, systematic effect that takes years to uncover. But sometimes, persistent discrepancies signal that our theoretical framework is incomplete. History offers examples of both outcomes. In some cases, anomalies vanished with better instrumentation. In others, they open doors to entirely new ways of understanding reality. The difficulty lies in knowing which situation you are facing while you're still inside it. The Hubble tension sits squarely in that ambiguous zone. From one perspective, the disagreement is modest. A difference of several kilometers per second per megaparsec may sound dramatic, but in absolute terms it is small. The universe is still expanding. Its overall behavior is well described. No observation suggests a catastrophic failure of cosmology. From another perspective, the disagreement strikes at the heart of the standard model of cosmology. That model rests on a delicate balance between different components: ordinary matter, dark matter, radiation, and dark energy. It has been remarkably successful in explaining a wide range of observations with a small set of parameters. The Hubble constant is one of those parameters. If that parameter cannot be made consistent across methods, then either one method is wrong in a way we do not yet understand, or the model itself needs adjustment. That is why the tension matters. One way to frame the issue is to ask where flexibility exists. The local measurements rely on astrophysical objects whose behaviour is complex but observable. Cepheids and supernovae are governed by known physics, but they exist in messy environments. Dust, crowding, and stellar evolution all introduce complications. If a hidden bias exists, it is most likely to hide here. Yet that is also where scrutiny has been most intense. The early universe inference relies on a theoretical framework that has passed many tests, but it is also more abstract. It extrapolates forward from a time when conditions were extreme and very different from today. If something unexpected happened in between, the model might not capture it. That flexibility cuts both ways. Supporters of the idea that the tension is a whisper often emphasize caution. They point out that cosmology has a long history of apparent problems resolving themselves quietly. They argue that no single discrepancy, especially one of this size, should prompt dramatic conclusions. Improved data from new instruments could still bring the numbers together. Supporters of the idea that the tension is a warning point to its persistence. They note that independent teams, using different data sets and methods, keep finding the same split. They argue that if the problem were purely observational, it would likely show more variation across analyses. Instead, the results cluster tightly around two different values. There is also an intermediate position, one that treats the tension neither as trivial nor as revolutionary, but as informative. In this view, the discrepancy is telling us something specific about the transition between early and late cosmic times. It may not require a complete overhaul of cosmology, but it may require adding nuance. For example, it is possible that the expansion history of the universe includes subtle features not captured by the simplest models. Perhaps dark energy does not behave exactly as assumed. Perhaps additional components influenced expansion briefly in the early universe and then faded away. Such scenarios would not overthrow the standard model, but they would extend it. This is why the phrase whisper or warning is so apt. A whisper suggests something faint but real, something that requires careful listening. A warning suggests attention is needed but not panic. The Hubble tension fits both interpretations depending on how one weighs the evidence. Another aspect worth considering is how the tension has shaped research priorities. It has not frozen progress or created division. Instead, it has motivated new measurements and new approaches. Astronomers are actively seeking alternative ways to measure expansion that bypass parts of the traditional distance ladder. Gravitational waves, galaxy clustering, and time delays in gravitational lensing are all being explored as independent probes. This diversity of approaches is healthy. It reduces reliance on any single method and increases the chances of identifying where the discrepancy originates. There is also a sociological dimension to the story. Cosmology is a field that has enjoyed remarkable success over the past few decades. Many of its major parameters were pinned down to high precision. The Hubble tension arrived as a reminder that precision does not guarantee completeness. That reminder has been taken seriously, but not emotionally. There is no sense of embarrassment or defensiveness. On the contrary, many researchers view the tension as an opportunity. It gives the field a concrete, testable problem to work on, one that could lead to deeper insight. It is also important to recognize what the tension does not undermine. It does not call into question the existence of dark matter or dark energy. It does not invalidate the evidence for cosmic expansion or the hot early universe. Those pillars remain solid. What it challenges is the assumption that our current description is final. From a listener's perspective, this can feel strangely reassuring. Science is often portrayed as a march towards certainty, but in reality it is a process of refinement. Moments like this, where certainty pauses and questions resurface, are part of that process. There is no shame in not knowing yet. In fact, the universe seems particularly adept at revealing its secrets gradually. It allows us to build models that work well enough to be useful, then nudges us toward improvement by exposing their limits. The Hubble tension may be one of those nudges. Another way to think about the situation is to consider scale. The early universe measurements probe conditions when the universe was extremely uniform. The local measurements probe a universe that has developed structure, complexity, and variation. It is not unreasonable to suspect that connecting those two regimes might involve subtleties. If so, the tension is not a sign of failure, but of transition. It is also worth noting that the language of whisper and warning is not meant to dramatize. It reflects uncertainty about interpretation, not fear. No matter how this resolves, the universe remains coherent. What changes is our description. As research continues, the tension may shrink. It may persist. It may even grow slightly as measurements become even more precise. Each outcome carries different implications, but none invalidate the careful work that has led us here. For now, the most honest stance is one of attentiveness. The numbers are telling us something. We do not yet know exactly what. That is not a problem to be rushed. The universe took billions of years to arrive at its current state. Understanding it may reasonably take time as well. Age is one of those ideas that feels simple until you try to pin it down precisely. For people, it is counted in birthdays and memories. For stars, it is traced through slow changes in brightness and composition. For the universe, age is inferred indirectly, stitched together from expansion rates, physical models, and the faint echoes of early conditions. When the numbers describing expansion refuse to agree, age becomes one of the first questions to wobble. If the universe is expanding faster today, then working backwards suggests it reached its current size more quickly. That points toward a younger universe. If expansion is slower, the same backward extrapolation stretches time out, implying an older cosmos. This is not a philosophical distinction. It is a mathematical consequence of how expansion connects distance, time, and scale. Under the standard picture, using early universe measurements and a slower present-day expansion rate, the universe is about 13.8 billion years old. This number is not arbitrary. It emerges from a self-consistent model that connects the cosmic microwave background, the growth of structure, and the observed abundances of light elements. Everything fits together neatly. Local measurements, however, lean toward a slightly faster expansion today. When that faster rate is folded into cosmic history, the implied age shrinks. Not dramatically, but enough to matter. The difference is on the order of several 100 million years. At first glance, that may not sound significant. Hundreds of millions of years vanish easily when talking about billions. But in cosmology, margins matter. The age of the universe must be consistent with the ages of its oldest inhabitants. Stars, globular clusters, and the chemical record of galaxies all place lower limits on how much time has passed since the universe began expanding. This is where the tension becomes tangible. Astronomers have studied some of the oldest stars in the Milky Way in exquisite detail. Their compositions, luminosities, and internal physics reveal how long they have been shining. Many of these stars are over 12 billion years old. Some estimates push close to 13 billion. These numbers already press up against the lower end of what a younger universe would allow. If the universe was significantly younger than these stars, the situation would be impossible. Stars cannot be older than the universe they formed in. While current local expansion rates do not force such a contradiction, they reduce the margin for error. An older universe, by contrast, offers more breathing room. A slower expansion rate today allows more time for stars to form, evolve, and reach the states we observe. From this perspective, the early universe value feels more comfortable. Yet comfort is not a scientific criterion. The question is not which age feels more intuitive, but which age is implied consistently by all available evidence. Right now, the evidence points in two slightly different directions, depending on how it's interpreted. One important subtlety is that age is not determined by the Hubble constant alone. The universe did not expand at a constant rate throughout its history. Early on, radiation and matter dominated, slowing expansion. Later, dark energy became important, speeding it up. The present-day expansion rate is just one piece of that story. This means that two universes with the same age could, in principle, have different present-day expansion rates if their expansion histories differ. Conversely, two universes with the same expansion rate today could have different ages if their past behaviour differed. This opens an intriguing possibility. Perhaps the universe is neither significantly younger nor older than currently thought. Perhaps its expansion history includes subtle features that alter how we connect early and late times. For example, if the universe expanded slightly faster than expected for a brief period early on, then slowed later, the present-day expansion rate inferred from early observations could differ from the local one, without dramatically altering the overall age. Such scenarios are actively explored. Another possibility is that dark energy does not behave exactly as assumed. In the simplest model, dark energy has a constant density and exerts the same influence over time. If its behaviour changed slightly, becoming more or less influential at different epochs, the expansion history would shift. Age estimates would shift with it. There is also the question of spatial curvature. The universe appears very close to flat, but even a small deviation could affect how distances and times are related. Current measurements constrain curvature tightly, but not infinitely so. Each of these possibilities offers a way to adjust age without discarding the entire framework of cosmology. Still, it is important to emphasize that no scenario currently requires a radical revision of cosmic age. We are not choosing between a universe that is 10 billion years old and one that is 20. The debate lives in the margins, but those margins matter because they test internal consistency. From a broader perspective, age is a derived quantity. It is not measured directly. It emerges from how we interpret expansion, gravity, and the contents of the universe. When those interpretations are challenged, age naturally becomes uncertain. This uncertainty is not a weakness. It reflects honesty about what is inferred and how. There is also a human tendency to treat cosmic age as a single, definitive number, when in reality it is better thought of as a range supported by different lines of evidence. That range has narrowed dramatically over the past century. The current tension nudges at its edges, but it does not blow it apart, as researchers explore whether the universe might be slightly younger or older than currently estimated. They are not rewriting the story from scratch. They are adjusting details, checking compatibility, and asking whether the same framework can accommodate all observations. One reason this matters is that age connects deeply to other cosmic milestones. The formation of the first stars, the emergence of galaxies, the build-up of heavy elements. These events have timelines inferred from observation. Any change in age must remain consistent with those timelines. So far, both the younger and older interpretations can be made consistent, but not without careful tuning. Another way to think about the question is to reverse it. Instead of asking whether the universe is younger or older, ask what kind of universe would produce the measurements we see. That shifts focus from age as a number to age as a consequence. In that framing, the tension suggests that something about the universe's expansion history is not being captured fully. Whether that missing piece affects age directly or indirectly remains open. For listeners, it may be reassuring to know that the universe's age is not suddenly up for grabs in a dramatic sense. The broad picture remains stable. What is changing is our confidence in the exact decimal places. There is also a quiet symmetry here. Early universe measurements look back to a time when the universe was simple and smooth. Local measurements look at a universe that has become complex and structured. Age is the thread that connects those two views. If that thread feels slightly stretched, it tells us to examine the weave more closely. Science rarely answers such questions by declaration. It answers them by accumulation. New data, new methods, new cross-checks. Over time, the range of possibilities narrows. As that process continues, the question of age remains a useful guide. It keeps attention on consistency. It forces models to account not just for expansion rates, but for the lived history of the universe's contents. Whether the final resolution nudges the age slightly upward, slightly downward, or leaves it largely unchanged, the exercise itself deepens understanding. It reminds us that even something as seemingly settled as the age of the universe rests on interlocking assumptions. Those assumptions are now being tested with unprecedented precision. Long after gravity had finished shaping the first galaxies and stars had settled into their slow, predictable lives, something unexpected began to matter more and more. It did not shine, it did not clump, it did not announce itself with explosions or radiation. Yet over time, it quietly took control of the universe's large-scale behaviour. Expansion, which had once been slowing under gravity's pull, began to speed up instead. The universe was not just growing, it was accelerating. This behaviour was not anticipated. For decades, cosmologists assumed that expansion, once set in motion, would gradually decelerate. Matter attracts matter. Gravity pulls things together. Even in an expanding universe, that pull should act like a brake. The more matter the universe contained, the stronger the braking effect should be. Expansion might continue forever, or it might eventually reverse, but it should slow. Observations disagreed. When astronomers used distant supernovae to trace how expansion behaved in the past, they found that the universe was expanding more slowly billions of years ago than it is today. That result was deeply counterintuitive. Instead of slowing down, expansion had been speeding up. Something was acting against gravity on the largest scales imaginable. The name given to that something was dark energy. Calling it energy was a choice of convenience, not understanding. Dark energy is not energy in the familiar sense of heat, motion, or light. It is a label for whatever is causing the expansion of the universe to accelerate. It does not describe a substance with known properties. It describes an effect. That distinction matters. Dark energy enters the equations of cosmology as a term that drives space to expand faster over time. In the simplest version of the theory, it has a constant density. As the universe expands and matter becomes more dilute, dark energy does not thin out. Its influence grows relative to everything else. Eventually, it dominates the cosmic budget. Today, dark energy accounts for roughly 70% of the total energy content of the universe. Ordinary matter, the atoms that make up stars, planets, and people, contributes only a few percent. Dark matter makes up most of the rest. This breakdown is inferred from multiple independent observations, including the cosmic microwave background, galaxy clustering, and supernova distances. In this standard picture, dark energy behaves like a constant background pressure, pushing space apart uniformly. It does not vary from place to place. It does not interact with matter in any detectable way, other than through gravity. It simply exists, quietly shaping the fate of the cosmos. This model has been remarkably successful. It explains why expansion accelerates. It fits the patterns seen in the cosmic microwave background. It matches the observed distribution of galaxies. For many years it appeared sufficient. Then the Hubble tension sharpened. If dark energy behaves exactly as assumed, then the expansion history inferred from the early universe should connect smoothly to the expansion measured locally today. The fact that it does not raises a natural question. Could dark energy be doing something more subtle? One possibility is that dark energy is not constant. Perhaps its influence has changed over time. If dark energy was slightly stronger or weaker in the past than it is now, the expansion history would shift. Early universe observations would infer one present-day expansion rate, while local measurements would reflect another. This idea is often described as evolving dark energy. In such models, dark energy might have been less influential in the early universe and grown stronger later, or it might have behaved differently during certain epochs. Even small deviations from constancy could have noticeable effects when extrapolated over billions of years. Importantly, these deviations would not necessarily disrupt other successful predictions. they could be subtle enough to escape detection in most observations, while still affecting the inferred Hubble constant. This makes evolving dark energy an attractive candidate for resolving the tension. However, attraction does not equal confirmation. Any modification to dark energy must satisfy strict constraints. It must preserve the excellent agreement between theory and observation in many other areas. It must not spoil the detailed patterns seen in the cosmic microwave background. It must remain consistent with how galaxies cluster and how structures grow. Designing such models is possible, but difficult. Many proposed versions of evolving dark energy have been ruled out as data improve. Others remain viable but unproven. Another idea is that dark energy might interact with other components of the universe, such as dark matter. In the standard picture, these components evolve independently. If they exchange energy or influence each other's behavior, the expansion history could change. Such interactions would be extremely weak, otherwise they would have been detected already. But even weak interactions acting over cosmic timescales could matter. This line of thinking opens the door to new physics, but it also complicates the theoretical landscape. Introducing interactions adds parameters. Each parameter must be constrained. The risk is creating models that fit one problem but fail elsewhere. There is also a more radical possibility. Perhaps dark energy is not a separate component at all, but a manifestation of how gravity behaves on large scales. In this view, what we call dark energy emerges from modifications to gravity itself, rather than from a new substance filling space. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy as a separate entity. Instead, they alter the rules governing how space and time respond to matter and energy. These theories are mathematically rich and conceptually appealing to some. They offer a unified explanation for expansion behavior, but they face serious challenges. Gravity has been tested extensively in many regimes, from the solar system to binary stars to gravitational waves. Any modification must agree with all of those tests. So far, no modified gravity theory has clearly outperformed dark energy models across the full range of observations. Still, the Hubble tension has renewed interest in these ideas. When a simple model struggles, exploring alternatives becomes worthwhile. There is also a less dramatic interpretation worth considering. Dark energy may be exactly what the standard model says it is, but its effects on expansion may be slightly misinterpreted when connecting early and late times. The issue may lie not in dark energy itself, but in how its influence is folded into models. This could involve subtle correlations between parameters or overlooked degeneracies in data analysis. In such cases, the tension might be resolved through improved modelling rather than new physics. What makes dark energy particularly relevant to the current discussion is timing. Dark energy becomes dominant relatively late in cosmic history. The cosmic microwave background captures the universe before dark energy mattered much. Local measurements capture the universe when dark energy dominates. If something about dark energy is misunderstood, the mismatch would appear exactly where it does, between early and late measurements. This alignment is suggestive, though not conclusive. It is also worth remembering how strange dark energy already is. Even in the standard picture, it raises deep questions. Why does it have the value it does? Why did it become dominant when it did? Why does its density appear so small compared to naive theoretical expectations? The Hubble tension does not create these questions. It adds urgency to them. From a listener's point of view, it can help to frame dark energy not as a mysterious force lurking ominously, but as a placeholder for incomplete understanding. It is a name we give to observed behaviour while we work toward a deeper explanation. In that sense, dark energy has always been provisional. Whether the resolution of the Hubble tension involves modifying dark energy, adding new components, or refining measurements, the concept itself remains central. Expansion is accelerating. Something is driving that acceleration. Understanding it fully is one of the major goals of modern cosmology. The current tension suggests that understanding may not yet be complete. That is not a cause for alarm, it is an invitation. Science advances not by clinging to comfortable models, but by testing them against increasingly precise data. When models strain, they either adapt or give way to better ones. Dark energy, as currently conceived, may survive this process intact, or it may evolve into something richer. Either outcome deepens knowledge. Speculation usually enters science only after restraint has done all it can. When measurements disagree, the first response is to question technique, calibration, and assumption. Only after those avenues are exhausted does a more unsettling possibility come into view. Perhaps the framework itself is incomplete. Perhaps the laws we rely on are accurate within familiar limits, yet subtly altered when stretched across the full scale of the universe. This is where discussions move beyond refinement and into extension. Not rejection of what works, but exploration of what might be missing. Einstein's theory of general relativity has passed every direct test thrown at it, with remarkable success. It explains planetary orbits, gravitational lensing, black holes, gravitational waves, and the large-scale behavior of space-time with extraordinary accuracy. For over a century, it has been the backbone of cosmology. Yet even Einstein understood that no theory should be considered final. Every theory has a domain of validity, and beyond that domain, new behavior may emerge. The Hubble tension has reopened a question that many assumed was settled. Does general relativity describe gravity perfectly on the largest possible scales? Or does it require modification when applied to the universe as a whole? This is not a new idea, but it has gained renewed attention. General relativity tells us how space and time respond to matter and energy. In cosmology, it is applied under assumptions of large-scale smoothness and uniformity. Those assumptions are well supported by observation. On average, the universe looks the same in every direction and location when viewed on sufficiently large scales. Within that framework, the equations predict how expansion should evolve given the universe's contents. When early universe observations are interpreted through these equations, they imply a specific present-day expansion rate. The fact that local measurements disagree suggests that either something is missing from the contents, or the equations themselves need adjustment. One class of ideas focuses on modifying gravity directly. In these models, general relativity remains an excellent approximation in familiar environments like the solar system or galaxies, but deviates slightly on cosmic scales. The deviations are designed to be small, subtle, and difficult to detect except through precise cosmological measurements. Such theories are not arbitrary. They are constructed carefully to preserve known successes while altering behavior where constraints are weaker. Some modifications involve adding extra fields that interact with gravity. These fields can change how space-time responds to matter over large distances without affecting local physics. Others alter the way curvature and energy relate to one another, effectively changing how expansion responds to the universe's contents. A key challenge for all such theories is consistency. Gravity is tested not just by cosmology, but by gravitational waves, binary pulsars, lensing observations, and the motion of galaxies. Any modification must satisfy all these constraints simultaneously. This is an unforgiving requirement. As a result, many proposed modifications fail quickly. They produce predictions that conflict with well-established observations. Others survive initial tests but struggle under more detailed scrutiny. A few remain viable, but none has emerged as a clear replacement for general relativity. Another direction involves introducing new components to the universe, rather than modifying gravity itself. One example is additional forms of energy or particles that existed primarily in the early universe. These components would affect expansion during that era and then fade away, leaving little trace today. Their influence could shift the inferred expansion rate without altering late-time behavior dramatically. Such ideas include additional relativistic particles, sometimes described as dark radiation. These particles would increase the expansion rate early on, changing how the universe evolved before the cosmic microwave background was released. When early universe data are analysed without accounting for them, the inferred present-day expansion rate could be biased. The appeal of this idea lies in its subtlety. The new components do not need to dominate or persist. They only need to exist long enough to leave a measurable imprint. However, these models face tight constraints. The cosmic microwave background is extremely sensitive to the amount of radiation present in the early universe. Adding even a small amount must be done carefully to avoid spoiling the excellent agreement with observed patterns. Another class of exotic possibilities involves interactions between known components. In the standard model of cosmology, dark matter and dark energy evolve independently. Dark matter clumps under gravity. Dark energy drives expansion. They do not exchange energy or influence each other directly. This assumption is made for simplicity, not because it is guaranteed. If dark matter and dark energy interact weakly, the expansion history could change in subtle ways. Energy transfer between components could alter how quickly structures grow and how expansion accelerates. Over billions of years, even a weak interaction could have noticeable effects. These interactions would be extremely difficult to detect directly. Dark matter already interacts very weakly with ordinary matter. Adding another weak interaction does not violate existing constraints easily. Yet modelling such interactions introduces complexity and uncertainty. As with modified gravity, the challenge is not imagining possibilities, but narrowing them down. There are also proposals that revisit the nature of spacetime itself. Some theoretical frameworks suggest that spacetime may have additional dimensions beyond the familiar three of space and one of time. In such models, gravity can leak into extra dimensions on large scales, altering expansion behaviour without affecting local physics. These ideas arise naturally in certain attempts to unify gravity with quantum mechanics. While fascinating, these models are speculative and difficult to test. Their predictions often depend on parameters that are not well constrained. Still, the Hubble tension has encouraged renewed interest in whether extra-dimensional effects could play a role. Another avenue involves questioning assumptions about cosmic homogeneity. While the universe is remarkably uniform on large scales, it is not perfectly so. Structures like voids, filaments, and clusters create regions with different densities. Some researchers have explored whether large-scale inhomogeneities could bias local expansion measurements. In extreme versions of this idea, a local region might be underdense or overdense in a way that affects how expansion appears locally compared to the global average. This could create an apparent discrepancy without requiring new physics. However, extensive surveys suggest that while local variations exist, they are unlikely to be large enough to explain the full tension. The universe appears too homogeneous on the relevant scales. What makes all these exotic possibilities difficult is not imagination, but discipline. Theoretical physics offers many ways to alter equations or add components. The challenge is finding ideas that are both mathematically consistent and observationally viable. This is why progress in this area is slow. It is also why caution is essential. History includes many cases where apparent anomalies inspired elaborate theories, only to dissolve with better data. Scientists working on the Hubble tension are acutely aware of this. At the same time, history also includes cases where anomalies pointed the way to profound advances. Mercury's orbit led to general relativity. Black body radiation led to quantum mechanics. In both cases, existing theories worked well until they didn't, and the discrepancies were small but persistent. The Hubble tension shares some features with those episodes, but it is too early to know whether it belongs in the same category. One important difference is that the current framework already includes elements that were once considered exotic. Dark matter and dark energy themselves were introduced to explain discrepancies. The standard model of cosmology is already an extended theory, built to accommodate observations. This raises a philosophical question. How much extension is reasonable before a framework becomes unwieldy? There is no simple answer. Science does not impose aesthetic limits, it follows evidence. If resolving the tension requires adding a new component, modifying gravity or refining assumptions, that path will be taken. What matters is that proposals are testable. Many of the exotic possibilities discussed are not vague speculations. They make predictions about other observables. They affect structure formation, gravitational lensing, or the growth of cosmic perturbations. As new data arrive, these predictions can be checked. This is where future observations become critical. Upcoming surveys and instruments will measure the universe in new ways, and with unprecedented precision. They will probe expansion using techniques that bypass traditional distance ladders. They will map structure growth across cosmic time. They will test gravity on scales never before accessible. If exotic physics is at play, it will leave traces. If it is not, those traces will be absent, and attention will return to more conventional explanations. From a listener's perspective, it is worth emphasizing that none of these ideas represent a rejection of Einstein in the everyday sense. General relativity remains extraordinarily successful where it has been tested. Even if modifications are needed on cosmic scales, they would likely reduce to Einstein's equations in familiar regimes. In that sense, new physics would extend Einstein rather than replace him. There is also a tendency to imagine new physics as something dramatic or unsettling. In practice, it is often incremental. Small terms added to equations, slight changes in behavior under specific conditions, subtle effects that become visible only when measurements are precise enough. The Hubble tension exists because measurements have reached that level of precision. It has exposed a seam in our understanding, not a fracture. As research continues, the field remains balanced between openness and skepticism. Exotic possibilities are explored seriously, but not embraced prematurely. Conventional explanations are scrutinized thoroughly, but not assumed sufficient. This balance is not indecision, it is method. The universe does not rush, and neither does understanding. Whether the resolution involves new physics beyond Einstein or a quieter correction within the existing frameworks, the process itself is revealing. It shows how far cosmology has come, and how carefully it now listens when the universe answers back slightly differently than expected. Before leaping too far into new physics, there is a quieter, more methodical question that insists on being asked. Have we misunderstood our own tools? When two careful measurements disagree, it is not reckless to imagine exotic explanations, but it is responsible to exhaust the ordinary ones first. In cosmology, that means returning to the instruments, the assumptions, and the subtle biases that can quietly shape results without announcing themselves. Systematic errors are not mistakes in the everyday sense. They are not typos or misreadings that vanish when corrected. They are biases built into methods, instruments, or interpretations that consistently nudge results in one direction. Because they act steadily rather than randomly, they do not average out with more data. In fact, they can become more convincing as precision improves. This is why systematic errors are so difficult to detect. In the context of the Hubble tension, the possibility of a misread cosmic ruler has been taken extremely seriously. Researchers have devoted years to asking whether local measurements might be skewed by effects that are subtle enough to survive multiple checks, yet strong enough to shift the inferred expansion rate. The local distance ladder is an intricate construction. It begins with parallax measurements of nearby stars, moves through Cepheid variables, and extends outward using Supernovae. Each step is grounded in physical reasoning, but each step also introduces opportunities for bias. Parallax, while conceptually simple, is limited by instrumentation. Measuring tiny angular shifts requires exquisite precision. Space-based observatories have improved this dramatically, but even small calibration offsets can propagate upward. A tiny systematic error in parallax distances could slightly miscalibrate Cepheid brightness, which in turn would affect supernova distances. This possibility has been examined carefully. Independent parallax data sets have been compared. Calibration strategies have been revised. Cross-checks with alternative geometric methods have been performed where possible. While refinements have occurred, they have not shifted the expansion rate enough to resolve the tension. Cepheid measurements themselves present another potential source of systematics. These stars often live in crowded regions of galaxies, surrounded by other stars whose light can blend with theirs. This blending can make Cepheids appear brighter than they truly are, leading to underestimated distances. Astronomers correct for this effect using high-resolution imaging and statistical modelling. Observations in infrared wavelengths reduce crowding and dust effects. Cepheids in different environments are compared. While blending remains a concern, its magnitude appears too small to account for the discrepancy on its own. Dust is another perennial suspect. Interstellar dust absorbs and scatters light, making objects appear dimmer and redder. If dust corrections are imperfect, distances can be misestimated. This issue affects both Cepheids and Supernovae. To address it, astronomers observe in multiple wavelengths and model how dust alters light across the spectrum. Again, corrections have been refined repeatedly. Different teams using different dust models arrive at similar expansion rates. This consistency argues against dust as the dominant culprit. Supernovae introduce their own complexities. Type 1 supernovae are standardized using correlations between brightness and light curve shape. These correlations are empirical, not derived from first principles. If they evolved subtly over cosmic time, distances inferred for distant supernovae could be biased. This possibility has been studied extensively. Supernovae in different host galaxies are compared. Environmental dependencies are examined. Nearby and distant samples are cross-checked. While small variations exist, they do not appear sufficient to explain the full difference in expansion rates. Selection effects are also scrutinized. Astronomers do not observe all supernovae equally. Brighter ones are easier to detect, especially at large distances. If detection thresholds bias samples toward intrinsically brighter events, distances could be underestimated. Statistical methods account for this bias, but no method is perfect. Multiple independent analyses, however, yield similar results. This suggests that selection effects are not driving the tension. Another class of potential systematics involves redshift measurements themselves. Redshift is usually extremely reliable, but local motions can complicate interpretation. Galaxies do not move solely with cosmic expansion. They also have peculiar velocities due to gravitational interactions. These motions can add or subtract from redshift, especially in the nearby universe. Astronomers correct for this by averaging over many galaxies and modelling large-scale flows. While peculiar velocities add scatter, they are unlikely to produce a coherent shift in the expansion rate. On the early universe side, systematic errors are also considered carefully. The cosmic microwave background is measured with extraordinary precision, but its interpretation depends on complex data processing. Instrument calibration, foreground subtraction, and statistical modelling all matter. Independent experiments using different instruments and analysis pipelines have been compared. Their results are consistent. Foreground contamination from our own galaxy is modelled and removed. Multiple frequency channels are used to separate cosmic signal from local emission. The remaining uncertainties are small. Crucially, the inferred expansion rate from early universe data is not a direct measurement, it is a model-dependent inference. This raises the question of whether assumptions built into the model could act like systematics. For example, assuming a specific number of particle species or a specific form of dark energy constrains how expansion evolves. If those assumptions are slightly wrong, the inferred Hubble constant could shift. This is where the line between systematic error and new physics becomes blurred. Adjusting assumptions may be equivalent to introducing new components. The distinction is not always clear. What has made the systematic error explanation increasingly uncomfortable is the way different methods agree internally but disagree externally. Local measurements agree with other local measurements. Early universe inferences agree with other early universe inferences. If systematics were dominating, more internal disagreement might be expected. This does not rule out systematics, but it narrows where they could hide. One intriguing idea is that multiple small systematics could align in the same direction. No single effect would be large enough to explain the tension, but together they might add up. This is possible, though it requires an unfortunate coincidence. Scientists do not dismiss this possibility. They quantify it. They ask how large each systematic would need to be, and whether such values are plausible given existing constraints. So far, the answer has been that such coincidences are possible but increasingly unlikely. There is also the question of confirmation bias. When a result becomes well known, researchers may unconsciously make analysis choices that align with expectations. This is why blind analyses and independent teams are so important. In the case of the Hubble tension, multiple groups using different methods and philosophies have reached similar conclusions. That diversity reduces the likelihood that a shared bias is driving the result. None of this means that systematic errors have been ruled out definitively. Science rarely rules anything out completely. It does mean that simple explanations have been tested thoroughly and found wanting. This is an uncomfortable position, but also a productive one. It forces researchers to sharpen their tools, improve transparency, and design new measurements that bypass known systematics entirely. Instead of refining the same ruler endlessly, they seek new rulers altogether. Gravitational lensing time delays, for example, measure expansion without relying on standard candles. Gravitational waves from merging neutron stars offer another independent route. Large-scale structure provides still another. Each of these methods comes with its own systematics, but they are different ones. Agreement across such diverse approaches would be powerful. Disagreement would be equally informative. From a broader perspective, the intense focus on systematic errors reflects a healthy scientific culture. Extraordinary claims require extraordinary care. Before embracing new physics, researchers are making sure they have not simply misread the universe using familiar tools. That care takes time. As listeners, it may be helpful to think of this stage as calibration of understanding rather than indecision. The universe is not ambiguous. Our interpretations are being refined to match its clarity. Whether the tension ultimately resolves through identifying a hidden systematic or through extending theory, the process is the same. Measure carefully, question assumptions, compare independent approaches. At present, the balance of evidence suggests that systematics alone are unlikely to fully explain the discrepancy. But unlikely is not impossible. As new methods mature and new data arrive, the role of systematics will become clearer. Some explanations will be eliminated, others will gain support. The cosmic ruler will either be confirmed or revised. And as that unfolds, attention naturally turns toward the tools of the future. If current instruments have reached their limits, what happens when sharper eyes and different techniques are brought to bear on the same question? Into this long-running debate stepped a telescope built not to settle arguments, but to see more clearly than anything before it. Its purpose was not to confirm one number or another, but to sharpen vision, to remove layers of uncertainty that had accumulated simply because earlier instruments could not see faint details well enough. Precision, after all, often changes the kinds of questions that can be asked. The James Webb Space Telescope was conceived as a successor in capability rather than a replacement in spirit. Where earlier space telescopes excelled in visible and ultraviolet light, Webb was designed to work primarily in the infrared. This choice was not aesthetic, it was practical. Much of the universe's most important information is hidden in wavelengths that visible light telescopes struggle to access, especially when dust, distance, or cosmic redshift push signals out of reach. Infrared vision matters enormously for measuring cosmic distances. Cepheid stars, for example, shine more steadily in infrared light than in visible light. Their brightness variations become cleaner. The effects of interstellar dust diminish. Crowding from neighbouring stars becomes easier to disentangle. All of these factors reduce systematic uncertainty. Webb's resolution and sensitivity allow astronomers to isolate Cepheids in distant galaxies with unprecedented clarity, even in regions that were previously too cluttered or too faint. This improvement alone has significant consequences. When Cepheids are measured more precisely, the calibration of the entire distance ladder tightens. That calibration flows upward to supernova distances, and from there to the inferred expansion rate. Webb does not introduce a new method so much as refine an existing one to a degree that was not previously possible. Another advantage lies in Webb's stability. Operating far from Earth, shielded from heat and stray light, the telescope maintains a remarkably consistent observational environment. This stability reduces subtle instrumental variations that can introduce bias. Measurements taken months or years apart can be compared with confidence that the instrument itself has not changed in meaningful ways. For a problem as delicate as the Hubble tension, this kind of stability is invaluable. Webb's role is not limited to Cepheids. It also observes the environments in which Type 1 supernovae occur. Understanding those environments better helps refine corrections applied to supernova brightness. Host galaxy properties, local stellar populations, and dust distributions can all be studied in greater detail. These refinements matter because supernovae are not abstract points of light. They occur in real galaxies with complex histories. Subtle environmental effects, once invisible, can now be examined directly. Importantly, Webb does not operate in isolation. Its measurements are compared against those from other telescopes, both space-based and ground-based. Agreement across instruments strengthens confidence. Disagreement highlights areas needing further scrutiny. Early results from Webb have been closely watched for signs that the local expansion rate might shift. If earlier measurements were biased by unresolved systematics, sharper data might pull the value downward, closer to the early universe prediction. So far, that has not happened. Instead, Webb's measurements of Cepheids appear consistent with previous results, but with smaller uncertainties. In other words, the picture has become sharper without changing its basic outline. The local expansion rate remains high. This outcome is not dramatic, but it is significant. Sharper measurements, reducing uncertainty without altering the central value, suggest that earlier results were not dominated by gross error. The cosmic ruler, at least in the nearby universe, appears to have been read correctly. That does not mean Webb has spoken the final word. It means it has narrowed the space in which certain explanations can hide. Webb also contributes indirectly by observing very distant galaxies and early star formation. While it is not designed to measure the cosmic microwave background, its observations inform models of how galaxies evolve, how stars form, and how structures grow. These processes connect local measurements to early universe predictions. Better understanding of galaxy evolution helps refine assumptions used in interpreting both local and early data. If subtle evolutionary effects influence distance indicators, Webb is well positioned to reveal them. There is also the matter of consistency across cosmic time. One lingering concern in cosmology has been whether objects used as distance indicators behave the same way at different epochs. Cepheids and supernovae observed billions of years ago might differ subtly from those nearby due to differences in chemical composition or environment. Webb's ability to observe these objects across a wider range of distances and conditions allows those questions to be tested directly. Again, the early indications are reassuring. No dramatic evolution has been detected that would undermine their use as standard candles. This does not eliminate all uncertainty, but it reduces plausible room for large unaccounted for effects. Another contribution of Webb lies in calibration itself. Parallax measurements from astrometric missions anchor the distance ladder at its base. Webb does not measure parallax directly in the same way, but it helps cross-check calibrations by observing objects whose distances are known through other means. Agreement across methods strengthens the entire structure. This cross-validation is crucial. The distance ladder is not a single chain, but a network. Webb adds new connections, making the network more resilient. From a broader perspective, Webb exemplifies how progress in cosmology often comes not from revolutionary ideas alone, but from incremental improvements in measurement, sharper images, cleaner spectra, better control of systematics. Each improvement reduces ambiguity. In the context of the Hubble tension, Webb's contribution has been sobering rather than sensational. It has not erased the discrepancy. It has not revealed a hidden error that explains everything away. Instead, it has confirmed that the disagreement persists even when observations are sharpened, that persistence matters. It shifts the burden of explanation. If local measurements remain robust under increasingly precise scrutiny, attention naturally turns elsewhere. Either the early universe inference must be reconsidered, or the connection between early and late times must be revised. This does not mean that Webb has solved the problem. It has clarified the landscape. Future observations with Webb will continue to refine measurements, larger samples, different environments, improve statistical power. Each dataset will tighten constraints further. At the same time, Webb's results feed into planning for other missions. Its findings inform where uncertainty remains and where new approaches might be most valuable. It is also important to recognize the limits of Webb's role. No single telescope can resolve a discrepancy that sits at the intersection of multiple methods and epochs. Webb is one piece of a larger effort, not a standalone arbiter. Still, that piece is an important one. The narrative arc here is subtle. Webb does not overturn previous work. It reinforces it with greater clarity. That reinforcement does not make the tension disappear. It makes it harder to ignore. For listeners, this can be framed as a sign of maturity rather than crisis. Cosmology has reached a point where tools are precise enough to test their own foundations. Webb represents the cutting edge of that precision. It also represents patience. The telescope was designed decades ago, built carefully, tested relentlessly, and deployed with extraordinary care. Its observations unfold slowly, methodically, each one adding a small piece to a much larger picture. That pace matches the nature of the problem. The Hubble tension is not a puzzle that yields to a single insight. It is a mismatch revealed only through accumulation. As Webb continues to observe, its role will evolve. It may not provide a direct answer to why the expansion rates differ, but it will constrain explanations more tightly. Some ideas will become untenable, others will gain plausibility. In science, narrowing possibilities is progress. As the space of uncertainty shrinks, attention turns increasingly to what remains viable. If sharper measurements continue to support the local expansion rate, then explanations that rely on local error become less attractive. The focus shifts toward global explanations. That shift does not happen abruptly. It happens through many careful studies, each one adding weight. Webb's contribution so far suggests that the local universe is being measured correctly, at least within current understanding. If that holds, then the universe may indeed be telling us that its expansion history is more complex than our simplest models assume. Suppose for a moment that the disagreement remains, not because we have failed to measure carefully enough, and not because some overlooked bias eventually reveals itself, but because the universe is genuinely doing something that our current description does not fully capture. If the numbers truly do not match, then the question shifts from how we measure to what we believe. This is where consequences begin to unfold. The first thing that would change is not a single equation or parameter, but confidence in the completeness of the standard cosmological model. That model has been extraordinarily successful. It explains a vast range of observations with a relatively small set of ingredients. It describes how the universe expanded, cooled, formed structure, and arrived at its present state. Yet success does not guarantee finality. If the Hubble tension reflects real physics rather than measurement error, then the standard model is not wrong so much as unfinished. In that case, the disagreement becomes a boundary marker. It tells us where the current framework stops being sufficient. One immediate implication would be that the expansion history of the universe is more nuanced than assumed. Right now, the model treats the transition from early to late times as smooth and well described by known components. If the present-day expansion rate inferred locally differs from the one inferred from early conditions, then something altered that transition. That alteration does not need to be dramatic. It could involve a brief episode early on when expansion behaved differently. It could involve a gradual change in how dark energy influences space. It could involve interactions that subtly reshaped cosmic evolution over billions of years. Any of these would require revising how we connect the early universe to the one we observe today. Another change would involve how cosmologists interpret precision. For decades, tightening error bars was seen as a path toward convergence. More data meant fewer disagreements. The Hubble tension challenges that expectation. It shows that precision can sometimes sharpen disagreement rather than erase it. This does not undermine the value of precision. It reframes its purpose. Precision becomes a tool not just for confirming models, but for exposing their limits. That shift affects how future experiments are designed. Instead of merely repeating existing measurements with greater accuracy, emphasis moves toward independent methods that probe the same quantity through different physics. Agreement across such methods would reinforce confidence. Persistent disagreement would strengthen the case for new interpretation. Another implication concerns how cosmology balances observation and theory. If the numbers do not match, theory cannot simply be adjusted freely to accommodate them. Any modification must preserve the model's many successes. This creates tension of its own. Changes must be surgical, not sweeping. This is why many proposed solutions focus on narrow windows of cosmic time or subtle effects. The universe cannot be changed wholesale without breaking other things that already work. In practical terms, this means cosmologists would need to introduce new parameters cautiously. Each new parameter increases explanatory flexibility, but reduces predictive power. Too many adjustments, and the model risks becoming descriptive rather than explanatory. This balance is delicate. There is also an implication for how cosmic age is discussed. If expansion history is revised, age estimates may shift slightly. That would ripple into discussions of early star formation, galaxy assembly, and the timing of cosmic milestones. These shifts would likely be modest, but they would require re-evaluating timelines that are currently taken as settled. Similarly, the inferred size of the observable universe could change subtly. Horizons depend on expansion history. A different expansion path alters how far light has travelled and what regions are causally connected. Again, these changes would not rewrite the universe dramatically, but they would adjust our sense of scale. Perhaps the most profound change would be philosophical rather than numerical. The standard model of cosmology achieved something rare in science. It provided a unified narrative that connected the earliest observable moments to the present day with remarkable coherence. If the Hubble tension persists, that narrative develops a seam. Seams are not failures. They are places where fabric can be extended. Accepting that the model is incomplete does not mean abandoning it. It means treating it as an approximation that works extremely well within known bounds, but not perfectly everywhere. Physics has lived with this before. Newtonian gravity remains useful despite being superseded by general relativity. Classical mechanics remains valid despite quantum mechanics redefining fundamentals. Each framework continues to function within its domain. Cosmology may be approaching a similar transition. If so, the change will not arrive as a sudden overthrow. It will arrive as addition, an extension that explains why two careful measurements tell slightly different stories about the same universe. Another implication lies in how dark components are conceptualized. Dark matter and dark energy are already placeholders for incomplete understanding. If resolving the Hubble tension requires modifying their behavior or introducing new forms of energy, it reinforces the idea that the universe contains ingredients we have not yet fully characterized. This is not a sign of failure. It is a sign that observation is outpacing explanation. It is also worth considering what would not change. The universe would still be expanding, galaxies would still recede, the cosmic microwave background would still reflect a hot, dense past. The evidence for dark matter would remain overwhelming. None of that is in question. What changes is the fine structure of understanding, not the foundation. From a practical standpoint, accepting that the numbers truly do not match would influence research priorities for decades. Resources would be directed toward probing the expansion history in new ways. Alternative theories would receive more attention. Data analysis would emphasize cross-method comparison even more strongly. Educational narratives would adapt as well. Instead of presenting the Hubble constant as a settled value with minor uncertainty, it would be presented as an actively investigated quantity with multiple operational definitions. That shift would not confuse students. It would reflect reality. There is also a cultural implication within science. Moments like this test how comfortable a field is with ambiguity. Cosmology, for much of its recent history, has enjoyed convergence. Parameters narrowed, models solidified. The Hubble tension reintroduces open-endedness. How that open-endedness is handled matters. If it is treated defensively, progress slows. If it is treated as an opportunity, progress accelerates. So far, the responses lean toward the latter. Researchers debate vigorously but productively. Competing ideas are proposed and tested. No single explanation has hardened into dogma. This is healthy. Another consequence involves time itself as a concept. Expansion rate links space and time intimately. If expansion history is revised, our understanding of cosmic time gains nuance. Time since the early universe may not map as simply onto present observations as assumed. This does not make time subjective or mysterious. It makes its measurement more context-dependent. Finally, there is the question of resolution. If the numbers truly do not match, resolution will not come from declaring a winner between methods. It will come from understanding why both are right within their own contexts. That understanding may reveal that the question, how fast is the universe expanding, has more than one meaningful answer, depending on how and when it is asked. This would be a subtle but important shift. Instead of a single expansion rate characterizing the universe universally, expansion might need to be described in a way that reflects its history more explicitly. Such a shift would not make cosmology less precise. It would make it more accurate. It can be reassuring to remember that science is not a quest for final answers, but for better questions. The Hubble tension may be forcing cosmology to ask a better question about expansion than it has before. Rather than asking for one number to rule them all, it may need to ask how expansion behaves across time and scale, and how different measurements illuminate different aspects of that behavior. If that is the case, then the disagreement is not a problem to be solved away, but a feature to be understood. Beyond numbers and models, what does it mean for us to live in a universe that still resists complete description? How should we relate to a cosmos that remains partially mysterious even under intense scrutiny? Somewhere beyond equations, instruments, and debates over decimal places, the universe continues doing what it has always done. It expands. Galaxies drift farther apart. Light stretches as it travels. None of this pauses while we argue about numbers. The cosmos is not waiting for consensus. It unfolds at its own pace, indifferent to whether our models are perfectly aligned. That perspective is important as we arrive here. After all the measurements, the disagreements, the careful scrutiny of methods, and the exploration of new ideas, it is natural to ask what any of this means beyond the technical details. If the universe is expanding a little faster or a little slower than expected, If its history is slightly different from our neat summaries, does that change anything about our place within it? In practical terms, almost nothing changes in daily life. The expansion of the universe does not tug at atoms, pull apart solar systems, or stretch bodies in space. Gravity holds galaxies together locally. Chemistry proceeds as it always has. Time flows at the same pace we experience now. The night sky looks the same to the naked eye as it did generations ago. Yet meaning does not depend on immediacy. The value of understanding cosmic expansion has never been about practical utility. It has been about orientation. Knowing how the universe behaves gives context to everything else. It situates human existence within a much larger story, one that stretches billions of years into the past and quite possibly trillions of years into the future. From that vantage point, the Hubble tension is not a flaw in understanding, but a reminder of scale. We live in a universe vast enough that even measuring its behaviour pushes the limits of knowledge. We infer its properties indirectly, using faint signals that have travelled unimaginable distances. The fact that these inferences mostly agree is remarkable. The fact that they disagree slightly is not shocking. It may even be expected. What matters is how we respond to that disagreement. One response would be to insist on closure, to force the numbers into alignment prematurely, declaring the matter settled. Another response, the one science tends to favour, is patience. Let the data accumulate. Let methods diversify. Allow understanding to mature without rushing it toward a tidy conclusion. The expanding future of the universe is long, in human terms almost absurdly so. If dark energy continues to dominate, galaxies beyond our local group will eventually drift so far away that their light will never reach us. The observable universe will grow emptier, quieter, simpler. Distant galaxies will fade beyond view, leaving only a few nearby companions visible in the night sky. This future is not dramatic. It is gradual. No cosmic event marks the moment when expansion becomes decisive. No sudden disappearance of galaxies occurs. Instead, over vast spans of time, the universe becomes increasingly isolated in patches, each bound structure drifting in an ever-thinning cosmic sea. From within such a future, cosmology would look very different. Observers, if any remain, would have far less information to work with. The cosmic microwave background would be stretched to wavelengths nearly impossible to detect. Evidence of a hot early universe might be inaccessible. In that sense, we are living at a privileged moment. Not privileged because we are special, but because the universe is still rich in accessible information. Light from distant galaxies still reaches us. Ancient radiation still fills space. The signatures of cosmic history are still readable. The Hubble tension arises because we can read those signatures in more than one way. That ability will not last forever. Understanding expansion now is not about predicting our fate in any personal sense. It is about using a fleeting window of clarity to learn as much as possible about how the universe works. The disagreements we see are part of that learning process. There is also something quietly human in this story. We measure, compare, and debate because we care about coherence. We want the universe to make sense as a whole. When it does not line up neatly, we feel compelled to investigate further. This impulse is not driven by necessity. It is driven by curiosity. That curiosity has carried us from a time when the universe seemed static and eternal to a time when we can describe its expansion, acceleration, and large-scale structure in detail. Along the way, we have learned that certainty is always provisional. Each generation inherits models that work well enough to explain what is known. Each generation refines them, extends them, or replaces them when new evidence demands it. The Hubble tension may mark such a generational transition, or it may resolve quietly into existing frameworks. Either outcome fits the pattern of scientific progress. What remains constant is the method, careful measurement, willingness to question assumptions, openness to multiple explanations, reluctance to declare final answers prematurely. These are not just scientific virtues, they are ways of relating to a world that is larger and more complex than any single perspective can capture. In that sense, drifting into the expanding future is not only a description of the universe, it is a description of understanding itself. Knowledge expands, models stretch, sometimes they strain, occasionally they tear and are mended with new ideas. The process is ongoing, and it does not end with a final page or a definitive number. Even if the Hubble tension were resolved tomorrow, new questions would follow. Why does dark energy have the value it does? Why did the universe begin in the state it did? Why are physical laws structured the way they are? Each answer opens new territory. For listeners, especially in a quiet moment like this, it may be comforting to let go of the need for resolution. The universe does not demand that we understand it completely. It offers patterns, signals, and hints. We engage with them as best we can. There is no penalty for not knowing everything yet. From a broader viewpoint, the fact that we can even ask these questions is extraordinary. We are small beings on a small planet, orbiting an ordinary star in an ordinary galaxy, and yet through patience and ingenuity, we have learned enough to notice when the universe's numbers do not quite agree with themselves. That is not failure. That is reach. As expansion continues, the universe will become colder, darker, and more diffuse. Structures will persist locally, but the grand connections will thin. In that distant future, the kind of cosmology we practice now may be impossible. Right now, it is not. Right now, the universe is still close enough, bright enough, and structured enough to be measured in multiple independent ways. The fact that those ways sometimes disagree is a testament to how far measurement has progressed. So what does it mean for us? It means we inhabit a universe that is still revealing itself. It means certainty is always conditional. It means understanding is something we approach asymptotically, never fully arriving, always refining. It also means there is no urgency to force closure. The cosmos is not a puzzle to be solved once and set aside. It is a process unfolding across time, inviting interpretation without guaranteeing completion. As you sit with this idea, there is no need to carry every detail forward. The numbers, the models, the tension itself can fade into the background. What remains is a sense of scale and continuity. The universe expands, knowledge expands. Both do so unevenly, sometimes smoothly, sometimes with friction. Neither stops. And somewhere within that vast quiet motion, we observe, measure, question, and occasionally pause, not at an ending, but at a moment of reflection, before curiosity naturally drifts onward, following the expansion into whatever understanding comes next.